Test, test.
Mic check. Cool. Sounds good.
Hey, welcome everyone to the Cloud Native Day Saturday at SCaLE. We're having a couple AV issues right now that we're figuring out, but we already got folks here. So in a short few moments, we'll be ready to go. I should have grabbed the microphone earlier, really, right, because that's clearly what summoned help. Thank you so much. Okay. You guys ready? Okay. Okay, anyway, with that, I would love to say hi and welcome to Tom and Lee. And please give both of them a big hand and welcome them to SCaLE. Thanks so much.
Hello, everyone. Hopefully, conference has been fun so far, and we're going to be talking about like containers and layers, and we're going to talk about NICs. And the idea behind this is to kind of inspire some thought and to give everyone a little bit of a sense of like, hey, like what are some things we can do? What are some possibilities? We don't really have all the answers, but just to kind of start conversations. That's kind of the whole point of this thing. We do have some ideas about where this can go and like why we're interested and passionate about this kind of overall topic, but maybe there's new things to be excited about that we don't even know about yet. So if something kind of strikes your fancy, please let us know, and well, we can do something and make something out of it. So I'm Tom Breckney. This is Lee Capilli. And let's get started. So that was us. We're going to talk about the OCI layer paradigm and maybe how to disrupt it. We're going to do this now. We just did a bunch of these sorts of talks over at Planet NICs. That was happening yesterday.
Check. Cool.
And now we're at SCaLE. I think, yeah. So let's get started. So containers. Containers are great. They're built from layers, but how many layers can you actually stack together? How do you orchestrate them? Uh-oh.
I was just trying to move that because maybe it was like an analog source that was causing the gain, the feedback. If I stand over here, I'm not getting feedback. If I stand next to Tom, we get feedback. Maybe it's because our mics are pointing at each other.
Turn off or something.
What if I stand here?
That might work.
That's probably, okay. So that's pretty impressive. Because yeah, it's like,
Excellent.
yeah, there it is. Okay, that's what does it. So Tom and I are, I guess we're like magnetically opposed.
Yeah, yeah.
Okay.
Okay, so yeah, so there's issues with when you have containers, sometimes with with how many layers you've got. Sometimes there's issues with size. Sometimes there's issues with orchestrating these things. Sometimes there's issues with startup. And there's issues of reproducibility. How do I compose them? And some of these things we can kind of fix or address, or like these are just pain points that we have. So we want to kind of start or maybe rethink some of these things and question some of our basic assumptions. That's kind of like the major kind of thought process here. All right, so overall ground rule for this, interrupt me. I do like having questions. I do like to, if something's unclear or if something could be more clear because you might have some insights or some knowledge that is better, then please interrupt no matter what. Otherwise, I will just keep talking and you will have to kick me off stage. So, okay, so we're going to talk about some of the limitations. We're going to talk a little bit about kind of how NICs works and how we think about things. We're going to talk about how OCI images are kind of normally put together, some of the practices that you might see. And then we'll go do a little bit of demo, a little bit of hands-on. We'll do some kind of QA afterwards and some discussion. So our intent here is to be a little bit informal as we go through. So containers. This is like fascinating stuff. It's like at the underpinnings of a lot of the advances we've made in terms of our ability to scale and like run and operate software, and it's like this is great stuff. We bundle applications, we bundle services. We're able to scale them out, move them around. We're able to test them, integrate them, isolate them, and there's a huge ecosystem built around this. Right, we've got products and conferences and monitoring and security tooling and terminology, careers built upon this technology. So it's kind of fundamental to a bunch of like the work that we do. But do we fully leverage them? Right? Are things we can kind of question? And I always like to kind of come up with ways. Can we like change something? Can we question some of those basic assumptions? So one of them that we kind of looked at a few times is that how do we build containers? We often build them in a very layered fashion. And do we have to? I don't know. So generally, when we kind of build containers, we do this, hey, we got a Docker file. we started writing up, hey, here's how I build my application. Here's my base image. I'm going to put my source in there. I'm going to start building stuff. And the way the caching works and the way we distribute these things, it kind of makes sense. We think about this as if this was broken down, layer by layer by layer. One thing building upon the next, a series of steps. This is simple, right? Each of these things then gets turned into a layer, and in our mental model, hey, they get turned into something that gets hashed, that gets tarred up, it gets sent up to a Docker registry, gets pushed around, and then those things get kind of burned in and baked. And this is kind of what works for us. Lee, you got it.
I just want to point out, for anyone new, and then also I think we've all become incredibly a lot of us have become very experienced with building containers, and so Tom said, oh, it's simple, it feels simple. But if you look at actually what's happening in the Docker file on the right, we for each layer, are writing a little script, or we're using a command from the Docker file syntax, from their little DSL. And that script or command is the local cache key for whether or not to rebuild that layer. And then the output of the layer is a content address hash. So that's how we know whether or not it changed, so that once we produce it, we have bits that are hashed, and we decide whether or not we want to send that layer somewhere else. And then the last thing that's really actually kind of special about this data structure is that for each layer, for all of our steps, we actually have a little bit of an order. So typically, we will invalidate this by the order, and we'll run all of the steps afterwards. And the reason that it is ordered is that a layer is actually an overlayFS file system layer. And that's really important, because it's going to do something for us that is kind of limiting. When we build an overlay file system with lots of layers, that has consequences. And I think it's really cool to look at this data structure, because it created a workflow that is so simple, yet so incredibly generic and powerful. And this is why containers are the shape that they are, and why we've built standards around them. But in order for us to move forward, we need to evolve, not away from this, but on top of it. And I'm really excited about that.
So yeah, as we summarized here, this is an amazing way of doing it. It's intuitive. It allows for really good adoption, right? People were able to kind of pick this up. It's a simple mental model, right? And it's effective. And then upon this, we now have a huge corpus of layers. We now kind of manage these things, in the millions. But there are some questions that are remaining, and these are the things that kind of I ask about. Is well, how do we share these things? Okay, we have mechanisms to move them around, but how do I share not the artifact at the end, but how do I share those Docker files, those instructions, those build instructions? How do I share those? Right? Do I just copy them around? How do I reuse them? What about bloat, right? This very kind of I'm always adding upon the previous layer is going to be very much you can imagine. You're always adding. You're never removing, right? How do we fix that? There's ways we do this in the industry, but again, it's not kind of built into the mental model that we normally have. How do we establish and enforce and check and make best practices easy to apply? Again, the simple mental model doesn't quite tell us, right? And that's fine. It's good for adoption, but again, how do we make this happen? How do we manage the supply chain? That's becoming more and more of interest for more industries. I mean, some of these situations, we started to build additional things. So then, hey, we added, multi-stage builds. This is a way for us to address some of these issues. Okay, some of them are very easy. Go is an excellent example. Everything gets compiled to one binary, and I can say, hey, go grab a base image with a bunch of stuff in it, add in some dependencies I might need, go bring in my project source code, go get all the dependencies that my project has, right? and then go compile this thing, and then I finally end up with one nice little artifact. And that little artifact, copy that over into my next container, and then now my build is complete, and I end up with something that's nice and clean. That's a really nice model, right? But again, even for this one, you can start to see that mental layer we had before, or mental model we had before is starting to break down. The whole, like, one layer for each of these in terms of what we're going to expect to see at runtime, again, it's not as clear. Now we're juggling different contexts, we're moving them around. Now this is probably the simplest possible example you could come up with, right? It's a language very nicely tuned to support this sort of a thing, and an ecosystem that supports it. But even this starts to kind of break that model. What happens when you have a lot more dynamic libraries or scripting languages where it's not so easy just to kind of to pluck out that one kind of artifact that you know that you need? What if you get it wrong, right? What happens if it's trying to like DL open something at runtime and then you know, things you expect to have there are gone, and only certain code paths do that? Who knows, right? Language-specific support I want to call out as interesting here because, well, different languages might not be amenable to this sort of thing. Again, then maybe some of them are, but then now you have to kind of have that expert knowledge of both your containerization technology and your language technology. So this is kind of these sorts of things help, but again, you know, what else can we do? So kind of take a quick pause on that. I come from an ecosystem where, you know, I'm fanatic about Nix. So if you want to go talk about Nix, I can do that for another few hours, but I'll try to keep it short and sweet here. Nix is a declarative framework, right? We like to do a whole bunch of like builds, package management, deployments, like in this kind of very you know, disciplined way. Been around since 2003. We got a whole bunch of like open source. We've eventually packaged all of open source, I'd say. And if it's not packaged yet, then it's likely because either it's too hard to package or because not enough people want it. But generally, everything's been out there. We have a big focus on like correctness, keeping track of provenance. So everyone worried about SBOMs. It's like, hey, this technology, this ecosystem has SBOMs just by construction. That's how we build the things. We worry about reproducibility a lot. You know, we call it purity. A lot of the best practices that you might want to impose upon your like ops teams, like, you know, as we do our builds of things, we do this by default. Like, you can't just call out to the internet at random and kind of grab things during your build processes. You know, you're not going to have some sort of like leakage into your system by like home directories and usernames and who knows what, like configurations that kind of leak into builds. We want to make all our dependencies very explicit, right? These are best practices that you kind of want to impose, but you know, here's a system that kind of does it for you or kind of enforces it. Sometimes that enforcement's a little strict, but again, it keeps you out of trouble most often.
I just want to point out a little thing, which is that earlier we mentioned that Docker is such a fantastic virtualization and runtime technology. And one of the reasons that it also became revolutionary is it became incredibly easy with the Dockerfile user interface for people to kind of package something that is runnable and maybe potentially even extendable, right? You could use base images and do some imperative stuff to then get to some other image that you want to run. But you'll notice that a lot of the problems that Nix solves that Tom is talking about here, Docker is completely unconcerned with. And I think what that points to is that Nix is an awesome packaging technology. And Docker images sort of accidentally became a packaging technology. But perhaps we can do better.
Yeah, thank you. So I gave the pros. Here are some cons. Basically, yeah, Nix is famous for a steep learning curve, but this is getting better, right? We're figuring out paradigms and abstractions that make it easier to learn. Documentation's getting better. This is the focus on upstream. I'm working at Phlox, where one of our goals is to kind of bring the power of this technology, but with a much, much simpler user interface to people. So drop by our booth, and that's my plug for the day. We also have a perception problem, right? We're kind of seen as very different and very niche, right? You're like, oh, you guys are like the weird kids over in the corner doing your kind of weird, crazy stuff. You know, came from the academic world and all this theory and all this functional programming. It feels weird to a lot of people. So we're going to work on, you know, being able to explain this better. and also be able to communicate better. There's also another interesting situation where there's a lot of like big companies, big enterprise users that kind of rely upon this tech, but it's funny that they don't come to conferences, they don't talk about it. It's interesting. It's sometimes it feels like they consider it like a trade secret. But we're seeing more in them come out about like what this is, be a bit more clear about it. They come to conferences. We started a blog series to talk about like, hey, like this actually is being used in the wild, and to start kind of raise the awareness of that this is a thing. We're running conferences, right? That's kind of why we're here. We ran one yesterday and the day before, and so we're trying to fix some of these issues. Okay, so what's this idea? Layers to graphs. That's like the kind of big picture CS kind of description of like what are we trying to propose here. Docker builds, right? Very linear, one by one by one. We have this ordered list. But normally when we build software, like when I'm building some piece of software, I don't usually think I'm going to take this one program and I'm going to extend it. I mean, that might be how I start, right? Or maybe that's kind of a plug-in style methodology. But usually it's like I'm going to take not just one program and extend it, or one library and wrap it or extend it. Instead, I'm going to take one library that does X, another library does networking, and another library that does like async work, another library that does image processing, and I combine them into some creation that works for me. I need multiple inputs, and I need to combine multiple things. That doesn't quite fit this like linear ordered list model, right? I can't just do like a leaf package, wrapping it, and then another leaf package, another leaf package. Instead, we usually think about like a tree of dependencies, a tree of libraries, things that depend on, right? When you do something like a Go build or an NPM build, this is what you get, right? And this is kind of how like Nix works as well. Nix kind of understands this like tree-like model, a DAG, right? This is a DAG that.
Yeah, all the computer science nerds were like, that's not a tree, that's two trees intersecting with direction. So the directed acyclical graph is what that DAG acronym means. It's a graph with pointers in one direction, and yeah, if you've never heard that term, it's no loops. Yeah, there's no loops in a DAG.
Yes.
Yeah, so you're always able to go from kind of the top of the multiple entry points in the DAG to the end of the leaf nodes of the DAG in one direction without repeating or cycling.
Yeah, thank you, yeah. This also, another thing that you get here, I want to just touch on slightly is when you have these sorts of, like here in this example, I got a portion of this graph that is kind of a little bit independent until it has to come together. That independence actually means I can distribute this. Let's say these things are very expensive to do, right? And on the right, you can see, hey, like this portion of those green boxes, I can actually distribute that work. So now imagine you could start to describe not just, hey, like a build of some software, something, maybe that build is very expensive, right? I can now start saying, hey, run some of these jobs on different machines or in different clusters and actually get distribution as a feature out of this, because I'm no longer forced to do things in a serial fashion. So that's something else to consider. Okay. This gets me into a kind of a thing that I care about is, in the end, like packaging. Like, what is packaging? And I think it's something that we sometimes think, oh, it's kind of this annoying thing to like actually get something into production or be able to distribute to other people. That's kind of the point. Packaging makes software reusable, right? Whether this is your end application, whether this is a library. I mean, we can hope that every single person out there is going to build everything from source, but frankly, that's probably not going to work, right? Most people just want their application. They want to just double-click. They want to download and roll. They want their existing package manager to just know how to install your application and upgrade it. So packaging is important. In some sense, I think we've abused and used containers as a packaging-ish format, but it's usually kind of a dead end. Like once you kind of put it into that container, now what? So if you make a library, should you just distribute that as a container? I actually talked to someone that did this, and it was a little confusing. I'm like, well, what if they need to use other libraries as well? Like, now what? And they're like, well, they're going to have to use our package manager. I'm like, okay, well, that might work for a little while, but how do you actually end up allowing people to reuse multiple things, right? So I think we still need packaging. Usually, if you go into a container or a Docker file, what do you usually see at the, very near the top? I'm going to apt-get install like 15 things for all my system libraries, or I'm going to like pip install all the requirements I need. Like, you're still going to use some other package management system to get it going. So in that sense, yeah, like containers kind of let us kind of cheat a little bit and get away with it, but at some point that cheating, that getting away with it's going to catch up with us. So yeah, so what else can we do? On the next kind of perspective of how we think about stuff, we'll say non-Nix world, we use like the file hierarchy standard. You put stuff into like user local bin or libs and all that stuff, and we use a different approach, right? We put everything into a set of store paths, and those store paths have like this cryptographic hash in there, and this way they're isolated. They're not going to be in your normal locations. And what this means is it's kind of like prepending everything with a content addressed hash, right, or a unique hash. And if you do that, now those files, those directories don't conflict with each other. So before, if you only have one thing in user bin, well, that's no longer a limitation because I've prefixed everything with this unique hash. Well, as we're talking about content hashes and things like that, that starts to sound like a container registry, right? If you think a layer, each layer is associated with some sort of a SHA-256 hash. Well, that's the same thing with like how we do things with directories. We just prefix it with that hash. Imagine if every single file that you used was prefixed with that hash, that layer hash that you might otherwise be familiar with from the OCI world, but it was just part of like the directory structure. What's nice about that is now it's not going to conflict. Now they're conflict-free because you're never going to rewrite them. You're never going to mutate them. So now it could be write-only. And this is how OCI layers work, right? So once you have a layer that has a particular content hash, well, you're not going to mutate it after that. That would change the hash. You still need to like take these things, and right now, the way we normally use OCI layers is you have to kind of do them in order because the contents can conflict, right? If you have two things in user bin called the same thing, and but they're different contents, now as you combine these things, you end up with a conflict, right? You have to kind of pick an order. You have to pick one to win. How do I distinguish between these things? But if inside of these layers, you were guaranteed that there was no conflict, then you have the possibility of doing all this stuff in parallel. I don't even have to check for conflicts because I know by construction there won't be. What's nice about this, for example, in the implementation of this, normally like layers, we use an overlay FS style, or we just kind of copy things on top of each other to generate what we end up using. If everything is conflict-free, I could just bind mount everything much, much faster. I don't have limitations. The 128 layer limitation that we have for layers kind of goes away. I can also reuse them a little bit better, right? Because now other people, it's not going to conflict with, maybe I know it's not going to conflict with me, but other people now also have that guarantee. And so you get much better reuse. And we have a bit more confidence they're not going to interact weirdly. I'm not going to overwrite something. I'm not going to end up deleting something and so forth. So this concept of a conflict-free layer as part of like the standard has promise. So where are we today? Right now, this is just meant to be like kind of like a reference slide. We can't go over everything right now. There's been a bunch of work of people exploring stuff. So kind of this history of this, a little while ago, there was like this blog post about, hey, how do we optimize Docker layers? And the idea was, hey, let's grab all these directories that are conflict-free, and let's kind of run them through a little bit of a like popularity, like topological sort contest, and that's one way to layer our containers. Let's grab all of them, as many as we can, until we run to the layer limit, and then at the very end, we'll just kind of put everything else into one like last final layer. We have people kind of working on things like, hey, how do we deliver containers kind of in a very dynamic way? The Nixery people did this. We started working on things like, how do we stream these builds, right? There's no reason to materialize them all at once into like your like local system. If I have all these directories, and again, they're conflict-free, I could do this in a streaming fashion. There's a PDT Partners did some work with this thing called Nix Snapshotter. This is so that you could run your Kubernetes in a way where the layers are actually grabbed and bind mounted in, right? That bound mount trick we talked about earlier is now used rather than overlaying all these layers. That gives you efficiency gains, it gives the ability in terms of like less storage, faster startup times. We wrote about like how this can kind of, how these containers and NICs are antithetical technologies, but actually can work together. There's some work right now in NICs packages where you can kind of apply custom strategies. So more complicated layering strategies can be applied, not just a matter of saying which one's more popular. Let's say you know for a fact a certain package or a certain kind of piece of content is going to be reused often. You could kind of extract that from the rest of the graph. Additional work. Replit did some work in terms of having how do we combine these things? How do we kind of get benefits of caching? Because they're trying to have large images, and a lot of their large images have a lot of similarities, and they started losing caching with their existing Docker file approach. And so by using this concept called overlay stores, they will get a lot of benefits, a lot of speed ups. So a lot of stuff to go read, a lot of references to go into, but people are exploring and designing kind of things along these lines. So here's a game plan. Let's make each directory a layer. Okay, that's one way to easily integrate with the existing technology, the existing frameworks. Sometimes run into problems here because, well, we run out of layers. Let's say you have something that's complicated, that's a large composition, some big ML framework, some AI stack. You might not be able to just say, hey, each package is its own layer, because you might have too many. Okay, well, what if I kind of combine packages, kind of create hey, here's a standard group, a standard chunk. I can start to fit within the layer limitations. Okay, that's nice. It's not as appealing as I would want it to be, but it's a tactic. I talked earlier about this custom strategies, right? We can say, hey, apply different strategies. I don't even know what strategies we might come up with, but that might be something we might want to do. All right. What else can we do? What if we just teach OCI about this concept? What if we just tell them? What if we just show OCI the manifest format, the runtimes that we have, that this thing I want to exist in my container can't conflict with any other similarly defined things in terms of the store paths and all that. And then now that limitation of how many layers I can use basically can just go away. Right? It can be implemented kind of inside the engine in a more efficient manner. So that's kind of upstream work that's making this kind of more of a standard. Oh, yeah. So the question was, why is there a limit on the number of layers? So the way kind of this was originally, there's different implementations, but the original implementations of how layers are implemented in the container runtimes use overlay FS. So they kind of give you one layer of a root directory, kind of tarball. They splat it out into disk and then go, cool, now you have another layer, but when you splat out the next layer, you have to check, well, am I overwriting something that already existed? Am I deleting something that existed, but with a little tombstone marker saying, get rid of it? Do I need to modify them? And so you have multiple of these overlay FS mounts on top of each other, and you can sometimes do this dynamically, or you can kind of materialize it as you go, but this becomes a slow process because it's very serial. You have to do it one by one by one.
Just again, going back to the mental model, right? Each one of these actually produces a file system. The file systems have to be overlaid on top of each other. So when Containerd or Cryo, your container runtime, or Docker, actually wants to go and get the OCI artifact that comes out of this, each file system actually has to be copied into a new overlay. And so even starting a container has a big kind of performance hit as you construct the container file system. But then even at runtime, this isn't free. So when you are reading a file or statting a file, any of the file system calls, in an overlay, you need to potentially traverse from the last layer all the way to the beginning to find what you're looking for. And so the mount system call for overlay has a limit to the number of these middle directories that you can mount. And it's because of that limit in the Linux kernel's implementation of overlayFS that then there is a canonical limit in all of the container tooling. And this is kind of just permeated and it is a trade-off. And what that means is that if we have software that depends on more than 120 things effectively, then we cannot represent all of those things as a layer. Unfortunately, any sort of trivial program that you might build could easily start to be 5,000 or 6,000 dependencies, or maybe even 20 or 100,000 dependencies. There's a question over there. The number being the layer limit. So that layer limit, again, comes from a limit to the amount of arguments that you can pass to the mount call on an overlay file system. Yeah, it is a little bit arbitrary, but it does have a performance cost.
Yeah. So,
and so we're going to get to how we can teach OCI about doing things in a non-conflicting way. The spoiler alert here is that what if we didn't use overlay? What if we used a bind mount instead? Containers we can already create with bind mounts, but you cannot construct an OCI manifest right now that tells something like containerd or cryo to do a bunch of bind mounts from some content addressable store. And so that's why we would need to teach OCI. Sweet.
yeah.
So
I mean,
that's a good diatribe on that.
you're right, though. Like, there is no reason that you can't kind of extend that limit, but if the system doesn't understand that these are non-conflicting, then it's going to have to check every single one on that list, and that's a very kind of yeah, actually, it slows down. Like that's a big piece of the startup time for containers. I don't have numbers at the top of my head, but I mean that limitation is there because in practice it was found to actually be a limitation. So they said once you get past a certain number, it starts to kind of not be practical anymore.
I'm not a Linux kernel developer, so I've only ever built kernels, not modified them. I imagine it's a non-trivial change to how overlay is implemented. But perhaps if you know how, we could get together and try. But it's actually part of the mount command.
All right. So next step on the game plan here. All right, we're going to need some tooling. We'll want to make tooling to make it so that packages are going to live in these immutable reference or in content address paths, right? Right. I told you earlier about hey, you could use Nix as that tooling to make that kind of easy. That's kind of the core way that Nix operates. But this is similar to there's other kind of systems out there that kind of do this sort of work to put things into their own locations and kind of distribute this. So this is not just Nix specific in terms of an idea, but this could be generalized. All right, what do we do after that? I don't know. Maybe other people have ideas. Maybe there's things that would be helpful here. And then after that, we profit. I'm really interested in steps 6 and 7. So if you have ideas on how to make that possible, let me know. OK, so we talked about this a lot in theory. Here's a little bit of kind of comparisons. If you kind of do this in this kind of fashion of putting everything into their own layer, you get some other interesting benefits. One of them is I can get rid of layers that I know I don't need, right? I can just start removing them because I have all these references to them. I know what they are. And I can start trimming things down. So this was an example that kind of someone showed us of, they built their Python application, but then we're done building it, right? They got rid of all their development dependencies, and what was left? The thing was, the number of packages you had were smaller. That's because we got rid of a bunch of things that only were needed during a build time or packaging time, and things roughly similar in terms of other metrics. But the big one that seemed to be of interest, and especially in some communities, the biggest interest is like your number of vulnerabilities goes down because you get rid of so much other stuff that might be there. And I mean, is that a huge difference? In some sense, yes, because vulnerabilities represent paperwork. It represents how many exceptions I need. It represents how many emails I get. It represents how many alerts I get or how much time I spend dealing with it. Even if I know for a fact that all 62 of the remaining ones are false alarms, I might have to go convince some auditor that that is. And that's might be more expensive than anything else I might do. And that might dominate. So one aspect of something we found along these lines is just let's reduce the amount of paperwork we do. It's not just technical optimization, but bureaucratic optimization. Something that I've talked about sometimes is you have like this difference between like the build time and runtime graph. Obviously, this is like the reason we have multi-stage builds. This is just kind of an example of like, hey, you almost always need a lot more to build something than just to run something. Obviously, there's some pathological examples where that's not the case, but generally, it's far less. Yep. Something to call out. We're going to have some similar topic about like optimizing image sizes later this afternoon. It's going to be by Brian Honoff, and go to his talk as well, because it's going to talk about this similar idea of how do I optimize images.
Is that 5 to 6?
5 to 6. Yep. Okay, so a little bit more about the layering strategies concept we talked about. There's a pull request in there that has some of the details of this is being worked on, but just to give people the idea of like managing a graph and slicing it and cutting it is kind of, how do you describe this? It's a little bit difficult to do. But this is something we're starting to work on is, hey, what if I want to like slice out of my dependency graph, in this case, Python? Well, you have to somehow explain, hey, like grab that and all the things it needs, slice it out. And then here what we're kind of showing is, for the rest of the graph, just run our like other standard like popularity contest kind of strategy. Then you can imagine like doing more complex things, right? You can pull out, hey, I want to pull out the standard platform for development that my company uses. That's going to be reused. It's not going to, it might have I might have some baseline that doesn't change often. Or maybe I do have a baseline that changes often. And so these different life cycles, I want to pull them out and kind of manage them independently. So this gives you a little more ability to like customize how layers are put together. Question? Yes, so right now this is like working within it, but you can also imagine this being applied when there is no limit. You still might want to do things like, let's say for transport purposes, you want these layers to be of similar size, so you can just process them and transport them all in parallel, right? Or maybe you just want this for grouping purposes. I want to group some of these together. So it might be reasons either way. Again, maybe we're in that kind of question mark part of the game plan, right?
I think like one interesting thing could be for like signing, if you wanted to combine layers and maybe you're like, oh, I want this particular blob of things that are certified to work together, and like maybe you want it all as one blob. But you could also just sign a manifest.
Yeah.
I mean, in the future, like assuming that parallel transport of a bunch of maybe also compression. Compression could also be another major reason, because as soon as you're separating a bunch of potentially similar things into large numbers of different blobs, then they have to be compressed separately, so unless you then, I guess, wrap them all up again and then maybe try to compress them again. So that could be another reason, is trying to balance compression versus separating each individual immutable thing for cache coherency. There was one more question.
Yeah, I'd like to go a bit back and challenge the whole thing. Like, when I build the images, honestly, I don't care about layers. And I want to have my distribution, right? I want to have my production image. I want to have my build image. Maybe a base image.
So I'm going to cut your question early because we're going to run out of time. The principle here, and I'm trying not to cut you off, I really appreciate what you're saying. It's very powerful. I'm going to try to make this point simple. The reason that Nix is really powerful with its binary cache is because each time you use one of those layers, if you're building complex graphs like this, then each dependency is immutable and it's cacheable. And even though you can reproduce it from source, you can rely on the work of a really big open source build server called Hydra. And if we were to cache each one of these layers, say you're building software on your Mac that requires 50,000 dependencies, or maybe let's just say 5, more realistic. And then you make an iterative change. Right now, when you build an overlay file system, your CPU must copy and compress each one of those bits of each of the 5,000 dependencies every single time that you build a new artifact, no matter how big or how small your change is. And then every one of those bits then gets pushed to a registry, probably from a CI system, and then it gets fanned out. So we are creating a lot of entropy and a lot of copies of the same exact bits over and over again. But if we can get to a place where the layers themselves are the individual derivations, you can pull down 5,000 things, change 10 things, only push 10 things instead of recompressing 5,000 things. And then when it fans out to potentially an entire open source ecosystem of millions of users, like say the Kubernetes base image, then all of those dependencies can be cache hit from stuff that's already there. And then each one of those derivations, or those OCI, content addressable blobs, does not need to be scanned again because of the immutable reference. And we're going to run out of time for a demo, so let's try to table the question to the end.
We'll have for 10.
Yeah.
You don't happen?
Huh?
Happen?
Yeah, are you going to skip the Docker tools?
Yeah, we'll do yours, yeah.
Let's go right to the Kubernetes stuff. Let's do this thing. So I don't need the HDMI, I just plug in the USB-C, right?
I think it needs the HDMI.
I have to use the HDMI? Where's the dongle? Here it is. All right, friends, I have something cool to show you. The first bit is a variation of something you've maybe seen before in other Nixie Kubernetes types talks. So, hey, maybe this whole layer thing might work out, right? So we had Tom talk about the Docker tools inside of the Nix libraries that you can use to build your own custom layer strategies. Works great if you're trying to stay within the layer limit. Tom and I were working on a proof of concept with folks who had a very large build cluster. And in that build cluster, what they wanted to do was have the power of Nix every time somebody created a build. And the build would run in a Kubernetes pod, and it would have access to some storage that you could get from somewhere, right? And so we built this initial demo with a read-only Nix store. Again, that Nix store, if you've never seen one, it looks, oh, hey, my pushes are all done. What a Nix store sort of looks like. Let's just close this here. So list the Nix store that I have on this GitHub code spaces. By the way, this code spaces is going to be in a repo after this if you'd like to reproduce our demos. So each one of these is a hash of some piece of software that is immutable that we got from the public build system. And like if I go and I can look at what's inside of, say, JQ, inside of Nix store. Right, so I've got a bunch of different JQ related things. Some of them are from different versions, and you can see that we sort of have this file system hierarchy type looking thing. Hopefully the text is large enough for folks to see, right? So inside of Nix store, we have some folder that doesn't conflict with the other things, and now we have a bunch of rootfs style things. You can see this data structure actually looks somewhat similar to a Docker file. the resulting OCI artifact. What if we found some way to get these folders into a pod a different way? And so the idea when we were working on this proof of concept was, let's first start with a read-only store. And if I'm just going to show the Kubernetes manifest, and again, we're going to push this into a repo. I have it running in a cluster as well. We'll see how much we can look at. This is the read-only store example. And we wanted to be able to mount that store from somewhere underneath. And then when we create our build pod, that we would be able to then pull other things from a Nix cache into the pod. And so this is a deployment with a build runner. The build runner creates a privileged mount manager because we need to mess with mounts. Technically, you could provide some more granular capabilities here, but this was just a proof of concept. This image here, we basically made a small base image with Nix in a different route so that it wouldn't collide with the things that we would be mounting a new Nix store from. And then we have a little shell script inside of the mount manager container here. And what it does is it makes an upper and a work directory for an overlay file system, and then mounts an overlay with a lower directory and an upper directory and a work dir. By the way, this is where that layer limit comes from, and it's what you would need to modify. Also, we're using overlayFS here, but I've heard that ButterFS does overlays maybe potentially in a more performant way, so that's also something as an aside that you could look at, is ButterFS. And then we would be able to touch something in that store and just make sure that we could add files. And we have some volume mounts in the mount manager where we are getting volumes from the host system. So what this means is that we need to land a Nix store on each of the little hypervisors or the little worker nodes inside of a Kubernetes cluster. So we grab the host data /Nix, call that the host shared Nix, and then we create an empty directory for the Nix in container mount, and then we also make an empty directory for an overlay file system. So the mount manager populates that overlay file system directory, and then it creates the Nix in container mount. And that mount propagates bidirectionally. And then for lifecycle, when this container stops, we have to unmount it so that we don't end up with zombie mounts on the system. Super hacky. Now we can create our user build container, which is unprivileged and not running with root. And then we hop in there, and we should be able to do Nix stuff as long as the volume mount has a read-only access to the Nix in container mount that the mount manager container just created. Now, how do we get the stuff from the host to be useful? Here we have a Nix host manager. We mount the stuff from the host. We are not using read-only access. We have write access to it now. So even so, like the container with the mount manager was doing everything read-only. But then here in the host manager, as a daemon set across all of our cluster nodes, we can then declare that we would like certain Nix packages to be there. And because we are using Nix, all of the dependencies of those packages will then populate inside of our Nix store across the Kubernetes cluster. I don't want to run out of time here to show you something super cool, so I'm going to leave it at this as far as the shared Nix demo. But you'll see that we have a different version here with overlay that has an overlay file system underneath at the host level, where we could also do read-write changes to the host store and then read-write changes in the containers at the same time. And this works. It's cool. You've seen similar demos before, potentially, if you've gone to other Nix-type, Kubernetes-type talks. Now I want to show you something also Kubernetes specific. Oh, and this runs in kind. You can see that if I get the namespaces on this Kubernetes and Docker cluster, we have a bunch of these proof of concept namespaces. Again, this will be in the repo if you want to reproduce. The next thing I want to show you relies on the cryo container runtime currently. It uses a feature that's currently in beta in Kubernetes 132. It's called image volumes. So with image volume, what we can do is we can actually create a volume that comes from a container registry. So we get the entire rootfs of some other container's overlay file system, and then we get to use Kubernetes to tell the runtime to pull that into storage if it's not present on the machine already, say for this pull policy, or you could say always. And then we can use volume mounts to mount that into some container of some pod and decide where that goes using a bind mount. Pretty cool. I thought, gosh, wouldn't it be nice if we built a demo for that using Nix? And that's what I've been doing this morning. I have this shell script that will create a deployment based off of, I think the base image here is Alpine Linux. We're just going to sleep forever. And then we've got a list of volume mounts. In the list of volume mounts, there's just some demo stuff. But then I'm also going to mount a database from a working Nix installation. And then we're going to loop over the store paths from Nix store. I have this limited to 260 paths, which I already know will work. But technically, I think I have 384 paths that I'm moving from this GitHub code space into a Docker registry as a bunch of individual container images. And then for each one of those store paths, I'm going to iterate a counter, create a volume for that counter, or this is technically a mount. I'm going to mount that volume at Nix store/store path. And then we are going to create the volumes list for the pod, and we have to have a matching volume. So again, for every store path in Nix store paths, let's make sure to keep the same counter in the same order on the same collection. And then we will grab an image volume with a reference to, on my Docker Hub account, StealthyBox, a repository called Nix store, where each tag of that container image is the rootfs looking thing from inside of Nix store on my GitHub code spaces. And then I have a little script, one for pushing var nixdb. So basically you copy star from nixdb, which is a build context, into the Docker image and just push it. And then same thing for a Nix store path. So you can say push path, some store path, and then it'll go and get that store path from the Nix store build context, push that up to your Docker registry. So you'll see if I pop over to StealthyBox Nix store on Docker Hub, then inside of my container image tags, I could say, look for kind. And now I have the binaries for Kubernetes in Docker at version 2.6 and version 0.27 with its hash as if it came from a Nix store, and this came from my GitHub code spaces when I ran that script. Similarly, I think I have a NixDB repo, and I just named this NixDB code space scale. So if I wanted to actually use Nix inside of the container and have a valid database for every path that I pushed, then that's like one way to do that. That means that if we run our script, which looks like this, gen deploy, and then we produce a YAML file, and then our script produces a Kubernetes deployment with a bunch of volume mounts to a bunch of Nix stores that there's 260 of them in here, so it's twice as much as the layer limit and more. And then for each one of those volume mounts, we have a matching reference to Docker.io, StealthyBox, Nix store, and then some Nix store path if it's not present already on the machine. So basically, if I do a kubectl apply, and then the file, and I do a deploy image volumes YAML, you'll see that I have an unchanged manifest here, which means that if I get the pods that are currently here. We have container creating. So what this means actually is if I describe that pod, I just sort of have a lot of store paths. It's like 2.8 gigabytes of, oh yeah, so I've reached my unauthenticated pull limit for Docker Hub because that's 260 different images. But then a bunch of these other ones are already present on the machine. Luckily, I did this earlier, but with 40 store paths. So if I show this one, which is already running, then I should be able to exec into it. So this running one, kexec, interactive. I'm going to start a shell session, and you'll see that if I go to /nix var nix db, I have the same database that came from my GitHub code spaces. And then similarly, if I go into Nix store and I do a little list, I've got a bunch of Nix store paths populated inside of my container. Each one of these Nix store paths comes from an independent overlay file system that was constructed for an independent container image that is all stored under the same repo. I've got, if I just like filter for one, which like most hashes should probably have a 1 in them, you can see that I've got 25 results per page, and there are currently roughly 13 pages. So that's 300 or so store paths on my Docker Hub account that I just pushed while Tom was speaking. And now I can actually go and run software. Maybe, do I have a bunch of libraries in here? There's only 40. Here's kubectl. Let's go into here, and there should be a binary directory, and I should be able to, oh, it's kubectl convert. I don't know what that is. Not sure what that is, but it's a binary and it runs and it works, and it's from the Nix store on my GitHub code space. It's that same exact store path. So there is one experimental way to get hundreds of different things beyond the layer limit into Kubernetes. And I would say that the only limit you're going to run into here is that usually with Kubernetes we don't like to store manifests that are greater than 2 megabytes. So if we look at how big the manifest actually is with 260 things, then it is 73 kilobytes. And yeah, that's constructing an image by abusing image volumes inside of Kubernetes, running them so that you can use your Nix software, and you don't have to have anything new. We don't have to change any standards in order for that to operate. My only criticism of this is it wouldn't scale to anything past 2 megabytes, so if you wanted to do like hundreds of thousands of things in a Nix store, then it probably would stop working because etcd just doesn't like that. And obviously this is not what this is for. I think this was produced, this feature became a beta feature that you can enable on a Kubernetes cluster because some people wanted to mount some like AI models, and I'm using it for this instead. But I think it's pretty performant. Mainly you need to be able to pull a lot of images onto a machine. If you're running your own Docker registry, that's not a problem. Or if you're pulling from GitHub instead of Docker Hub, that would be perfectly fine. And then also I'm unauthenticated. So if I authenticated with Docker Hub, I wouldn't have the rate limit. And my last criticism of doing this is we shouldn't need Kubernetes to be able to tell a container runtime to bind mount a bunch of content. And so that gets into sort of the last point, which is we can do a node local NIX store by sharing var NIX, or /NIX from the host. We can do image volumes where we can push NIX databases and NIX store paths independently as container images that you can then reference, and you can use Kubernetes or a similar orchestrator to do a bunch of bind mounts. This demo would be really cool, and you should go to Brian's talk at 5 o'clock. NIX Snapshotter extends containerd, which is one of the options for container runtime, so that you can get store paths directly from a NIX daemon. And the way that it extends containerd is by adding annotations to the OCI manifest to tell this special piece of software where to find the paths. And you can mix these NIX store paths directly from a NIX daemon with regular overlay layers from standard OCI images. This would be a cool thing in the future, especially for development, where you have a NIX daemon and containerd running on the same machine. But a glimpse of the future would also be then a similar piece of logic that is standard in containerd that does not need any NIX protocol so that you could actually ship your artifacts, and it would also work for like RPM OS tree and those kinds of things. But yeah, that's pretty much most of our homework on figuring out how we can make cloud native NIX a thing. And we are over time a little bit, so we should probably close this out. Call to action is let's bring reproducibility, flexibility, and efficiency to containerized workflows. Kubernetes gives us an orchestration layer. It also gives us this weird alpha or beta feature that we can use to maybe even construct images in a NIXy way. How could we put those things together to do real cloud native NIX? Be really cool. If we have time for questions, Tom and I would love to talk to all of you about it, and of course, also freedom to the SCaLE organizers to kick us off stage. What do you think, Gwen?
Thank you so much for your presentation, first of all. Second, we have 10 minutes to set up the next speaker, so if you all want to chat, move it to the hallway track, please.
Tom and I are going to stand outside that door.
Hey,
Thank you, everyone.
Stay around for our next talk. Should be another good one. Always backfires for me because I wear dresses.
Let's try this. Can you hear me?
Test 1, 2.
Batteries if you're changing them.
Oh, these are fresh here?
I don't know.
Okay. I think this is, yeah, we left 4, so test 1, 2, test 1, 2. Just stand. Okay, test 1, 2.
Hello, test 1.
2.
Test 1, 2.
Test. I'm gonna cross
They
behind you.
said they were standing here.
Test 1, 2. Test 1, 2. Okay, maybe if I'm just gonna try every scenario here. Test 1, 2. Test
Yeah, I don't
1,
know.
2. Okay. Cool. You mind if I just walk in front of you real quick?
No,
to
yeah,
see?
go
Okay,
ahead.
Test 1,
Yeah.
2. Test 1, 2. Test 1, 2. Okay. Yeah, I turned down the gain a little bit, so you shouldn't have that problem. But I'll once the session starts, I'll kind of monitor.
Okay, we'll start in a minute.
All right. Okay, fantastic. Welcome everyone for this 12:30, almost lunchtime talk. I am super excited to introduce Jonathan Perry today, who's here to talk to you about better latency with fewer servers. Let's give him a hand. Thank you so much for being here.
Thanks everybody for coming to this talk about memory noisy neighbor. I'll start with this. Have you seen this YouTube video? It's called Positive Affirmations for Site Reliability Engineers. Anybody? It's a really funny video, and I recommend that you watch it. I'm not going to do it justice, but it goes something like this. The video starts in the evening. A lone site reliability engineer sits at his desk. He's seeing exceptions thrown in production, the rising cost of the deployment, and is just feeling so frustrated and overwhelmed. He meditates. A calming female voice tells him, "Your pipeline is green. Your tests are well written and stable. Your friends and family understand what you do. You were born to deploy Kubernetes." And so I recommend you watch it, but this made me think, why do we choose to operate these large deployments? And for me, the ultimate affirmation is your deployment is highly available and cost efficient. Users delight in the product and its performance. And I think this is the holy grail, what we're working towards. And so let me talk a little bit about performance. Companies understand today that performance has a major impact on their business outcomes and on user satisfaction. You're probably all familiar with the 2006 Amazon published results, where for every 100 milliseconds of added latency, they lost 1% of revenue, which is amazing. But there have been multiple other case studies showing similar results over the past few years, and there are recent ones. There are dozens of them, and I just brought the brand names that I recognized, and I think everybody would. You can see Google, Akamai, eBay, Yelp, and Adobe. And so you can read those similar results. I really like the one on the bottom from Rakuten 24 in 2022. It's a Japanese online grocery store, and they ran an A/B test with the exact same functionality of the application, but sent 50% of their traffic to an optimized application and 50 to the old application. And for just 400 millisecond difference in latency, they saw 53% increase in revenue per visitor and 15% in average order value. It's kind of amazing. So can we understand that performance really matters? And yet the other side of the equations that users love is having a great product. And users expect a lot more functionality from our products. They want recommendation systems, they want search, they just want more data to display so that they can make better decisions. In general, just more features. And while your deployments might not be as complex as these extreme published cases, still your deployments probably have quite a bit of functionality. And it becomes a lot harder to reason about performance when you have this much functionality. It actually becomes easy to blame the spaghetti monster of complexity when it comes to performance degradation. And you can, frequently hear people say, oh, it's the network, right? So kind of we have these amorphous entities that we have very little visibility into or control over that kind of we blame. But a lot of the performance degradation comes from simple resource contention on the servers our applications run on. It's simple as that. So it's not an amorphous thing, and we can solve that. And so what if I told you that a small cabal of engineers got together and built a secret resource allocation capability that allowed them to run 20 to 50% more efficiently on less hardware, and improves their tail latency by factors of 4, 5, or 13. That would be fantastic, right? Kind of how can we not know about this kind of huge advancement? Well, it turns out this capability was actually, seems to actually have been built, and the development was not in secret at all. Over more than a decade, there have been papers from hyperscalers and well-known universities exploring this capability. So today I want to give an overview about what's known about memory noisy neighbor. And the reason I'm giving this talk is I believe that there's enough knowledge out there so that this can be made into practical systems for the Kubernetes community. I've divided the talk into 5 sections. First, I'll discuss what memory noisy are and how they manifest in our systems. Then, why should we care? What are the benefits we're going to get if we mitigate them? What are the hardware and software mechanisms that are available and what are their limitations? Then, what systems have been built and been published, and so how to think about building these types of mitigation systems, and then talk about our current efforts. I'm Jonathan. I did my PhD in noisy neighbor mitigation, specifically network noisy neighbor mitigation. I then founded a company called FlowMill, which built eBPF-based network observability tooling, got acquired by Splunk, and the collector is available as the OpenTelemetry network collector. I'm an OpenTelemetry maintainer. And I started Unvariance to tackle noisy neighbor in the cloud. So let's start with the problem. What is memory noisy neighbor and how does it affect my pods? And actually, do I actually have it or not is a major question. Our cloud native applications run on physical hardware eventually, and these applications share the finite hardware resources that our servers have. In noisy neighbor, one application consumes more than its fair share of resources, and so the other applications running alongside it have a hard time getting those resources and so experience degraded performance. In this talk, I'm going to focus on the memory subsystem, which is the last level cache, which I'll just call cache, and memory bandwidth. Let's dive into it. This benchmark shows, the benchmark varied how many reads and writes to memory it performed over the course of the benchmark. So it changed how much memory bandwidth it consumed, and it measured on the y-axis memory access latency. And as you can see, as the benchmark progresses, as the benchmark puts more and more memory bandwidth pressure on the system, the memory access latency increases until at around 80%, if you look at the 90 gigabytes per second mark there, the increase in access latency becomes a lot more substantial with an increase in memory bandwidth. What this means is if you have one application that drives the system from the, into the regime of the 80 to 100% memory bandwidth, then suddenly all of the applications on the system start experiencing high memory access latency. You can look at the numbers, almost double, actually double or more. And so this is noisy neighbor, right? And one application causing degradation for all the other applications. You might ask, CPUs have all of these mechanisms that are meant to hide memory latency so that applications don't experience degraded performance. For example, prefetchers try to read memory from RAM onto the CPU ahead of time, so when the CPU needs it, it's already there. The reorder buffer allows the CPU to execute later instructions, while a previous instruction is waiting for memory, so it can do useful work. And caches keep data around so that it doesn't need to be reread from RAM over and over. And the question is, are these mechanisms actually effective in hiding memory latency, or is performance going to degrade if this happens? So to measure how much an application slows down due to memory access latency, a common metric is cycles per instruction, or CPI, and I'm going to use this metric throughout the talk. The idea is this: when the CPU has to wait for memory, it incurs these stall cycles. So to if there's memory pressure, memory reads are slow, then to execute the same amount of instructions, it is going to take more cycles because it incurs these stall cycles. So the ratio of cycles per instructions is going to be high. If there's no memory contention, no stall cycles, few stall cycles, then the total number of cycles for the same amount of instructions is low, the ratio is lower. So let's look at some measurements. Alibaba published these measurements in 2022, and they measured a cluster with 8,000 nodes in production with over 1 million containers. And they sampled these low-level metrics like memory bandwidth, memory latency, and cycles per instruction on every context switch over 24 hours. What you can see here on the left is a similar graph to what we saw in the benchmark, but this was measured in production, where on the x-axis is memory bandwidth, and on the y-axis is access latency. So you can see with an increase in memory bandwidth, the access latency increases, and then there's the knee around 80%. On the right side here is another graph showing on the x-axis the memory access latency, and on the y-axis the slowdown. And this shows that actually, when there is an increase in access latency, there is a slowdown in applications. In these clusters, what a noisy neighbor means is when you have a noisy neighbor that drives the memory bandwidth the last 20%, you're going to see a doubling in memory access latency, and so a 25% increase in cycles per instruction. So just think about it for a minute. Having this one noisy neighbor causes everybody else on the same system to incur 25% more cycles to execute the same amount of work. CPU looks like it's high, but if you're not measuring memory bandwidth, you don't know that the applications are not doing useful work. They're just stalled waiting for memory for 25% of the time. Now, these measurements were done with cache noisy neighbor mitigation. So this only shows memory noisy neighbor mitigation. Now let's look at cache noisy neighbor mitigation. The effects can be a lot more dramatic, even than that. So here's how an application might fit into the cache hierarchy. You have the blazing hot working set in L1 cache, and then the hot, warm, and cool working sets fit into the L2, L3, and DRAM. And you can see the access latencies here from 1.5 nanoseconds on the L1 cache to 4, 21, and then DRAM, we said, it varies based on how loaded it is between 85 nanoseconds and 250 nanoseconds. What happens when a noisy neighbor arrives is it evicts. It has a lot of of memory reads, and so it evicts your application out of the shared L3 cache, and now that your application needs to read its warm working set out of DRAM. So what would have taken 21 nanoseconds now might take as much as 250 nanoseconds, so a 10 times difference just there. In the more extreme case where your noisy neighbor lives in the hyperthread next to your core, so the virtual core next to your virtual core, it might evict your application from L2 cache. So now even the hot working set needs to be served from DRAM, and this is very substantial, right? From 4 nanoseconds, it becomes 250 nanoseconds. It's more than 50 times difference. And your hot working set might be 75% of all your reads and writes, right? Like it is the hot working set. So 50 times on a major part of your reads and writes. So this can be very substantial. And in fact, it has been measured to be very significant. Google published this paper in a paper called Heracles in 2015, where they measured production Google workloads. You can see the 3 tables here are the three production workloads. Web search is the search node from Google. ML cluster is text classification service that works on users' requests, and memkeyval is an in-memory key value store like memcache. The rows in these tables are the different noise generators, and you can see one for baseline no noise generator, and then 3 cache noise generators, the small, medium, and big, and the memory bandwidth noisy neighbor. The columns here are load on the system, and the numbers are the tail latency as a fraction of the target SLO, so the target P95 or P99 latency. They didn't publish the numbers. They didn't, I don't, it's probably kind of a trade secret that no one would publish their SLOs, but they published the fraction of SLOs. And so you can see both, all 3 workloads have very significant increases in tail latency. The web search experiences more than 4 times increase. ML cluster more than 5 times, and the memcache equivalent more than 13 times increase in tail latency. So this is very substantial on real workload. So I want to run a small survey here. Please raise your hand if you know, maybe you're working with a production cluster and you know the node types that the cluster holds. So what types of VMs? Is it bare metal? Is it the extra large? Is it the 8 cores, 16 cores? Do you know a production cluster and what type of nodes are on there? Okay, now please leave your hand up if you never use a fraction of a physical CPU. You never use the 8 cores or 16 cores. You always use either bare metal or the full CPU. Anybody? Nobody here. Right, so we tend to use the smaller VMs. So consider this. Best practice today is to separate our batch workloads from our production, user-facing, latency-sensitive workloads, right? We don't want somebody to run a batch analytics job and just destroy the performance on the user-facing workloads. And it turns out, if you're running this way, and you're running in the cloud, and you're using not the full CPUs, but taking these fractions of 8 cores here, 16 cores there, then it actually looks like this. Your workload is running next to other people's potentially batch analytics. Right? And so while you've done all of the work to separate your own clusters, your own batch analytics from your own latency-sensitive workloads, you're actually running next to some random organization on the internet, their batch analytics. So it's actually like this. Does your cloud provider protect you from memory noisy neighbor and adjacent VMs? I haven't been able to find evidence that they do. And in fact, there's a little experiment at the end. Don't want to spoil it, so you'll see later, there's more. So consider engineers spend months and sometimes years optimizing the deployments, right? Like they might create database indices or change them. They might change the storage schemas in the databases so the queries run faster. They might take services and break them to multiple services so that parts of the queries can run in parallel. And can do profiling and alleviate bottlenecks. And all of that work can just be erased, obliterated by some memory noisy neighbor running next to your VM and just making the whole compute node slower. And so if you're running a system with, let's call it more than 1,000 CPU cores, then you should prefer to run on a few 100-core bare metal machines rather than a lot of these 8 cores or 4-core machines. This way, at least you know that your noisy neighbor is going to be workloads that you know, your own workloads that are latency-sensitive production workloads and not the batch analytics workloads, which tend to be a lot more memory-intensive. And so the question is, okay, so let's say we did that. Do you need to have batch analytics to see noisy neighbors? So if I don't run batch analytics next to my workloads, will I see noisy neighbor? And the answer is probably you will, because a lot of workloads are noisy neighbor. In this experiment run by MIT researchers in 2020, they ran memcache alongside a garbage collected workload. And you can see on the top graph here the memory bandwidth. As the experiment starts, it's pretty low. And as the mark phase of the garbage collector starts, memory bandwidth is saturated. The mark phase is very memory intensive. And if you look at the latency in the bottom graph, it's usually at around 50 microseconds tail latency. It's P99.9. And then as the mark phase starts, latency spikes more than 3 orders of magnitude, more than 1,000 times. This shows even garbage collection can be a noisy neighbor in your system. And there are other examples of memory-intensive workloads. So, for example, video streaming and transcoding. When container images arrive to your system, they come compressed. So decompressing container images is memory-intensive. And just generally, if you're running a service, many services have these cases where once every few minutes, a user request arrives that touches a lot of records. A very expensive user request that can take 500 milliseconds, that could be, memory intensive and a noisy neighbor. All right, I get a question a lot about AI. So usually GPUs have their own memory, and they communicate between GPUs using dedicated links like NVIDIA NVLink or InfiniBand. But during both training and inference, the CPU and DRAM have important roles in both. So in training, the CPU needs to read the training data from network or disk, then usually does some pre-processing, tokenization, and then has to send these micro batches to the GPU for training. And these can be, multiple gigabytes per second of transfers. And so these responsibilities compete. And if there's other things running on the systems, all of those compete for DRAM. The same thing goes for inference time. So in inference time, the CPU needs to feed the inputs to the GPU and collect the outputs, do some tokenization, handle batching and communication with users, and all of these can compete for DRAM. And so memory bandwidth. And so if any of you in the audience, if you have a use case for measuring GPU memory bandwidth, please let us know, because we're thinking about how to build this as well. Although for now, we're focusing on the CPU side. So to recap, memory noisy neighbor shows up as high memory access latency, which translates to these high cycles per instructions, which mean it just shows up as the CPU has high utilization, but it's not doing useful work. Tail latency suffers, and we've seen 4 to 13 times increase. And you can get noisy neighbor from either VMs running alongside you, but also from your own workloads. So why should we care? Why would we need to solve the memory noisy neighbor problem? And what benefits could we get from it? So here's a survey that Datadog publishes showing that a lot of the containers that we run use very little of the CPU that we request for them. And so I want to run another survey here to maybe duplicate this. And so please raise your hand if you know the utilization of a production user-facing cluster. Okay, a few hands here. So please leave your hands up if it's more than 20% CPU utilization. Okay, most. More than 30? Most? More than 40? Okay, everybody took their, most, a half, 3/4 took their hands up. More than 50? More or less, okay, one or two people. Okay, I want to talk to you, it's really interesting. So if you said 20 to 40%, you're in very good company. Some of the largest companies on the planet with big engineering teams that are able to optimize their deployments have published average CPU utilizations between 20 and 40%. But what seemed to have happened over the last few years is that a handful of companies have been able to increase their utilization substantially. So Google was 35% in 2011 and 50% in 2019. So if you consider the difference, that's a lot, 50% more workload. So reading published work, there seems to be at least two contributors. The first one is advancements in vertical auto-scaling, so setting the memory and CPU requests just right so that less resources are wasted. And the second one is handling noisy neighbor, which enables companies to run with fewer cycles per request, reduce tail latency, and so run hotter. And so how do we scale, usually? You can either have a set number of replicas manually on your deployments, or you can be using an automatic scaling system like the horizontal pod autoscaler. And that looks at metrics like CPU utilization or requests per second. But how do you set the threshold for these mechanisms? How do you choose how many replicas a service would have? Or how do you choose what are the CPU utilization targets when the horizontal pod autoscaler scales up and down? Well, it seems today this is more of an art. You run with some thresholds, you measure the SLOs, and then you adjust. If your system is not hitting your SLOs, then you maybe reduce your CPU targets. If the system is, churning along great, maybe you increase the CPU targets so that you run more efficiently. And what this means is that if we can dramatically improve the SLOs, we can reduce the tail latency, then we can adjust these thresholds to run hotter. And we can get a lot more out of the servers that we're running on. What could we do if we had this? Well, one thing we could do is we could reduce cost. So run the same workloads on fewer replicas that each one runs hotter. What you can do, another thing you could do is you can try to implement more features into your product. So now you're running the same number of replicas, but with more functionality, and so they're running hotter because they're executing more codes and producing more value to users. And last, you can just say, okay, let's roll the benefits to the users and have them give them improved SLOs, so give them better tail latency. And what Google, for example, did is they were able to run a lot more workloads on the same hardware. And so this brings us to, again, to our holy grail. It allows us to make the system more cost efficient, or improve the product, or improve the performance, or a mix, right? Like we have this leeway where solving memory noisy neighbor gives us better tail latency and so freedom to do all of these three and gets us closer to the holy grail. Okay, and with that, I want to switch a little bit to how do you do this, right? What are the tools that we have available? Modern CPUs allow direct control over how much of each of these resources an application uses. You can decide what fraction of the cache each application can use and how much memory bandwidth it is allowed to use. The other method that does to control memory noisy neighbor that does not require hardware support is by limiting the opportunity that the noisy neighbor has to produce noise. So you can pin the noisy neighbor to a handful of cores and limit the number of cores that you pin it on and adjust their frequency so that it runs slower. So basically you can choke the noisy neighbor or reduce the number of cycles that it has, because as the noisy neighbor has less cycles, it can produce less noise in the system. And I'll say something similar later. So we use this in another system that I'll talk about in a couple of minutes. So how does this look in terms of hardware interfaces? The CPU has different identifiers that can be used there are two types. There are resource measurement IDs, RMIDs, that are used to measure cache utilization and memory bandwidth, and there are enforcement or allocation IDs called classes of service or CLOSs. And the idea is this, you can think about it as coloring your workload. On every context switch, the operating system tells the CPU, here now color all of these memory accesses blue. And so the thread goes around and accesses memory, and later you can ask the CPU, how much of the cache is blue? and how much of the memory bandwidth we used recently was blue. And so you have enough of these colors in order to measure different entities. CPUs have a limited number of those IDs. So on the M7i on EC2, which is a recent Intel Xeon machine, it has 96 cores and 448 RMIDs, and 15 allocation IDs, the CLOSs. So if you're trying to measure individual threads and you have thousands of threads, then there aren't enough colors and there aren't enough IDs. But if you have 200, 300 containers running on this 100-core machine, then you should be able to monitor each one of them. And some of these CPUs also support what I talked about for AI, measuring GPU to DRAM bandwidth as well. So you might ask, you know, I would expect the containers would have already provided this for us, right? Like this hardware has been around since 2016. Why do containers not have it? Yeah, we have CPU and memory containers. They should have it, but they don't. They deal with other resources. And in fact, when Intel wanted to contribute this code into the kernel in 2016, kernel maintainers thought it wasn't a good fit for C groups, so they put it into another subsystem called res control, or resource control. And the idea was they wanted threads to be able to ask for their own allocation. So it's like with CPU sets, where threads can say, I want to only be allocated on these CPUs and not those CPUs. They wanted threads to say, I need this much cache. They thought that would be a good use case. And so C groups was not a good fit for that. And together with the hardware having a very limited number of, not very, but a limited number of identifiers, this means that, you know, you can't have arbitrary number of containers. They didn't want some unpredictability there. And so it ended up in this subsystem that you can access through the kernel file system in sysfs. I'll show you a quick demo. I didn't record this. Credit goes to TJ Hale and collaborators at Meta who recorded this, called the Facebook Resource Control demo. Let's see. Give it a minute. There it is. Okay, so here you can see a workload is starting. In green is the number of transactions per second, and in blue, the latency. Now you're going to start a noisy neighbor, which is a compile job, on the same node. And you can see how the requests per second drops, latency increases. Let's close the compilation job and have the workload reconverge. And now we'll start the noisy neighbor, that same compilation job, with resource control. And you can see performance is still all right, like the same that you'd expect, but the compile job is running in the background. You can see it, but everything's running okay. Hypervisors have some support for memory and cache allocation, but there is just such a scarcity of documentation. And from the documentation that is out there, it seems that a lot of the use cases are these very specific niche use cases that require very, very strict isolation of workloads, for example, in telco and in finance. All right, so we saw that there is hardware support for direct allocation of these resources, and we saw that Linux has support. So how do we build a full system that can mitigate noisy neighbor? So I'll go through these three major types of systems, and if you read papers, most of the systems fall into these three categories. The first one is one based on cycles per instruction. So we already talked about this. When the CPI is high, then there's it indicates that there is a lot of memory contention. When it's low, everything's okay. And so these systems utilize that. The problem is that you don't know what is a good CPI and what is a bad CPI. Is 3 good? Is 2 good? What should I do? And it varies by application because applications have different memory access patterns. And so these systems measure the CPI for each task and construct these profiles of what is, you know, regular, how the task usually looks like in terms of CPI. the system then uses these profiles to detect outliers. And an outlier suffering from noisy neighbor is one of these tasks that has an outlying CPI, high CPI for multiple measurement intervals. So once you detect the outlier, kind of this application suffering from noisy neighbor, you try to detect to find which is the noisy neighbor. And what the system does is it uses that same property we talked about before, where if a noisy neighbor has more CPU, it can generate more noise. If it has less CPU, it can generate less noise. So what it does is it correlates the CPU utilization of every other task on the system with the CPI measurements of the outlier to detect which is the noisy neighbor correlated that is probably generating this high noise. And once it does that, it can limit the noisy neighbor. The major issue with these systems is that CPI is a very noisy measurement because it depends on whether in which section of code you're running in, right? You need to average it over multiple seconds. And by the time this system makes a decision, you know, a lot of damage has already been done. And in many cases, at least in the interactive cases when you have user-facing data, many times the noisy neighbor is no longer noisy by the time the system detects it. It's good if you're running kind of big data analytics and you don't want the big data analytics to conflict, but for user-facing traffic, these are just not effective. The other disadvantage the system has is that it needs to create these profiles. So you need a centralized component that collects these measurements, aggregates them, and then distributes the profiles down to the per server components so that they can do the outlier detection, and that is more complex. But according to Google, in a 2013 paper, as of the paper writing, this had been deployed to all of Google's shared clusters. So it seems like this was running in production. I talked to some Google engineers. Seems like this was actually working for them, more for the more persistent noisy neighbor problems. Let's move to the second type of system, which is latency control. So we want to have applications tail latencies to be to meet their SLO targets, right? So if we can measure them and then allocate resources so that to meet latency targets, that'll be great, right? Like that's what we're trying to achieve. So what these systems do is they measure latencies at the application layer and then compute the percent of the SLO target that the application is running at. So maybe one application is at 50% of its SLO target, or its P95 latency target, and another application is at 98% of its latency target. So it's really about to breach its SLOs. And then it then finds the slowest task and the fastest task, and then moves resources from the fastest task to the slowest task. So you can think about it as a
there to see, could you build a gaming system this way? Then in March, I got involved trying to build something that we could do for the server, hoping to be something for home, but also maybe even business would want to use. And then this year, we had our newest addition with Aurora, which is like a KDE-based spin similar to Bluefin, and here we are. So it's been more than 2 years of activity in our project.
Yes, it's been quite busy. So we want to talk about a little bit of what is Universal Blue, because we really haven't answered that yet. So it is a layered image architecture. The idea is that we start from a main repository, which includes basically those minimal changes, quality of life things to make computing on the desktop much more doable. And so we include hardware support, we include NVIDIA drivers in there, and we have all of these different things that eventually create Bazite and Bluefin. We have our packages repo, which are custom RPM packages distributed through Copper, as well as our friends over at Fear Labs who have Terra. they allow us to be able to, focus on that user experience and being able to actually improve things for us. And then additionally,
Yeah, so one of the things you mentioned, Maine includes a lot of hardware support enablement through UDEV rules and things like that are bundled. But pretty early on, NVIDIA was probably the first driver that we were trying to add that was a challenge to get into an atomic desktop system. And so we started building, pre-building all those for whatever kernels that are shipping on the image. And that's in our AK mods repo. And now there's like more than 20 kernel modules that are in there to support different bits of hardware, a lot of it for gaming handhelds, et cetera. And then more recently, Bazite itself has building a patched kernel that adds a lot of support that they need for that hardware.
yeah,
All of that comes together to make the final images that we're shipping out.
we are basically a platform for you to be able to build off of. That's the general idea, is that, we want to take that hard stuff and remove those obstacles so that you can get to work on your custom image. So we want to talk about our philosophy a bit here of when I said in the beginning, one desktop, one OS, is the idea of having a single model for the Linux desktop. And a lot of people, say immutable and that sort of thing, and the only thing that is immutable about our project is our will to make this happen and make it move forward. You want to go into the cloud native?
Yeah, we say cloud native a lot, and one of the key goals has been to build this in a way that makes sense for anyone who's building software out in the community, or rather in the industry. That's actually how I got involved, was seeing, like, wow, these guys are building a Linux system, and I can have a reproducible build that I can do on my own if I wanted, because we're just using GitHub Actions and Docker or Podman, and I've got something that I can not worry about breaking when a system update happens. But we're doing it using these tools. We've tried to be really approachable to new contributors, myself included, Noel, new contributors. There's been quite a few, obviously, to make a project work.
And I think, just to add on to that, a lot of us at the Universal Blue Project, this is basically our first contribution to Linux, myself included. When I started working with Universal Blue, I didn't even know how to use Git, which is kind of funny because I use it every day now. And really, it's that opportunity to be able to learn new skills and opportunities that I think is so powerful about this model and what we have built.
Yeah.
And yeah, you want to go or me? So I think the other point of it too is that cloud native technology powers the world. I mean, that's just the reality of things. Data centers, all of these different things, Kubernetes, are all cloud native projects, and we really want to bring those to the desktop and make it as stable and as useful as those projects are in the cloud. So, and the other focus too, which is awesome about the cloud native community, is the ability for us to be able to have a safe and welcoming space, which the path has been paved by a lot of these projects like Kubernetes and other projects that exist in the cloud native space. And so I think that's something that is really important to us and core to our philosophy. Do you want to talk about Bootsy?
Sure. So when we first got started building Universal Blue images, there was no Bootsy. We were definitely using Podman and Builda technologies. But everything was built on the Container Native initiative on top of RPM OS tree. So the technology that was powering Fedora CoreOS and the atomic desktops like Silverblue and Kinoite. This has been continuing to get developed. Podman Bootsy projects recently were contributed to the CNCF. And what it's really let us do is build these images that it's like a Docker application that you're packaging, except it's your whole OS. And we've seen so many times where this technology has allowed us to save the day because either there's a driver bug or a kernel bug and it's easy to roll back, or we simply have a failed build up in the cloud because of that thing that would have crashed your system and messed up your RPM database in the past.
And I think that rapid iteration point is key. I mean, being able to make it approachable so that, a user reports a bug to us and they say, oh, I'm having this problem with this specific piece of hardware, and then I can very quickly spin up a container or even push a change almost immediately to our infrastructure or to a testing branch or anything else, say, I need you to use this, go ahead and see if this works, or I can try to replicate it on my end. That makes that far easier. And so I think that's something that's so powerful about Bootsy and the bootable containers. If you're familiar with containers, it is basically a container with systemd and a kernel. That's really the main big differences. We want to give users what they want, and what they want is FlatHub. What they want is a way in which to be able to have applications that they need packaged in a way that is accessible. And FlatHub has definitely, in my opinion, been the best way of doing that. It allows us to be able to have that sandboxing from a security perspective. It allows it to have developers have control of those pipelines to be able to make changes that are quick and iteratable. And the other cool thing is that FlatHub has discussed the idea of how it is important to provide economic stability and sustainability for developers by allowing, the idea of being able to purchase applications, which is a very new thing. When you think about your phone, for example, you can buy applications. There are free ones that are available, and they, in my opinion, are the leaders in doing that and making that be something that is functional across the Linux space.
Yeah, and as we were actually preparing this, I made the comment, which I think is still appropriate. Although there's a lot of excellent philosophy and thoughts that are really important in the free software community, sometimes I'm just a little bit simpler, and I just want a simple experience. And that's what we get by having FlatHub enabled out of the box is, there's a really nice line here, an easier than Windows install solution for new users. And my kids, my whole family runs Bluefin-based desktops, and it's really easy. That's all I wanted, is to make it easy.
Yeah, we want to make open source approachable and usable and as easy as, your phone or your tablet or anything else. We believe in the idea that using existing infrastructure and using already people who have trailblazed good practices of doing things is a good idea. It's just inherent to being able to more quickly develop, more quickly iterate, more quickly be able to get the things that people need. And the things that we utilize are GitHub Actions. Our entire project is built inside of GitHub, minus a few things, externally, but for the most part, it's primarily GitHub Actions, Fedora Copper. Cloudflare is the way in which that we distribute our ISO images, and then we have repositories from Terra, Negativo, and RPM Fusion, which allow us to have an even wider selection of software to be able to select to make that experience easier out of the box. And the crazy thing to me is the fact that this project costs less than $100 a month to run because we do everything out in the open, which I think is just unbelievable. So.
It's probably true of a lot of open source software, but really something that means a lot to us is we know we're standing on the shoulder of giants. Everything that we're building is just a little bit opinionated, a little bit nicer, trying to create that experience, but it's because of the hard work of the communities around Fedora, CentOS, Fedora CoreOS, Bootsy, Podman, and we enjoy doing it. But one of the things we've also tried to do is keep giving back. So we have been able to put different contributions back, whether it's something small into ZFS or something into CoreOS. We've had a kernel contribution. So we're trying to continue to foster that two-way contribution.
Exactly, yeah, and the idea is that we want to focus on the things that are working. We don't want to have these tribal fights, this not invented here syndrome, just because we didn't do it, you know, oh gosh, it's not as good or whatever the case may be. It's that not invented here syndrome is not what we're about. We want to use the trailblazing, the standards, what the industry has decided is a good idea at the moment. And again, giving back, like Mr. Sherman had said, it's the idea of really trying to focus on fostering that relationship with upstream as well as the things that we do in our own community. So we want to talk about, so we've talked about what Universal Blue is, and we want to talk about why this model works and why we think more people should very highly consider using this, either our project or building their own things based on us, or even just using the upstreams that we use and building their own things. It's explosive growth. I look at this chart and I can't believe it, to be honest. How old our project is, how recently I feel like I joined the project. Like I almost feel like a newbie, you know, sometimes. Like, you know, folks that have been in the project, like I've only been, you know, last 1 to 2 years, I think, at this point, and like really how we have grown. And the thing that I think about, which is funny, is that I was walking around the booths and my first SCaLE was last year. And I'm here giving a talk now, which is crazy. I never thought that would happen. But I think the other thing is too, is just the amount of people that I walked around and mingled with and talked with, and they're like, oh, you're a speaker, you know, what do you do, you know, and stuff like that. Well, I work on this little project called, you know, Universal Blue, and we do this container, you know, cloud native thing. And then I say one word, which is Bazite, which there's a talk later. You absolutely should come to that one, because it's gonna be awesome and gamery. But like, I would say the word Bazite and people are like, oh yeah, I love that project. I run it on my home theater PC, or oh, I love that project. I have it for my gaming handheld or something like that. And just to see how the community has kind of come around the ideas and things that we are doing, in my opinion, is proof that we are doing something right, at least. And so.
And one of the things, because we're using these industry standard tools, it's also providing an opportunity to give some light to the companies that are involved in the development of those, and they've given back. We've got contributions from a wide variety of upstreams, and you know, we've also been able to help some of our contributors be involved in developing their own careers. Learning the industry standard tools gives them a better career path, and we've actually had a few cases where we've been able to get people new job opportunities. So it's been really good from a community perspective to be helping others gain opportunity.
Those are the proudest moments for me, really. You know, there's the moments of realizing how this project has really changed my life, just personally, and just seeing the excitement of the opportunities that others have been able to get. And I think that's like something that's so important with an open source project, is to think about, like, how can I help the next generation? How can I get people to where they want to be? And I believe in this mission of what we're doing and how it benefits our contributors, as well as making the Linux desktop space better. You want to get on me?
Yeah, sure. So we've talked more about the background, and you've got the clicker, so.
Yeah.
We just want to talk a little bit more about what are the unique experiences that are provided by what we're building. So here we have Bluefin and Aurora, GNOME and KDE. A lot of this is focused around a developer experience, but it's really more like a generic desktop experience. The developer-specific experience does include tools for Kubernetes, virtualization with QEMU and KVM, VS Code and dev containers are built in, Tailscale, Homebrew, Docker, all kinds of monospace fonts, set up scripts to make AI easy and ready to go. there's a whole lot there. I mean, so much I'm a little bit overwhelmed when I run that sometimes. We also just try to make sane defaults, so you can just install it and start working, and which I actually needed to try to use Windows a little bit recently, and I was really shocked by how hard it was to get things going again, and it's reminded me I really love the project we're building. So
Yeah, it out of the box, like if you install Bluefin, or Aurora, in case you're a KDE fanboy like myself, you really just get that out of the box experience, like I just want to start getting work done. I think that's so valuable. The other experience, which is our largest growth that we have seen by far, is the gamer experience, which is Bazite. And you can learn more about that today in room 105 from 5 to 6, where Kyle and I will be talking about this. And what is so cool about Bazite is, like, for me, like, I had a dream when I was a kid that I would, like, work at Nintendo or something, or work at, PlayStation, Sony, like working on making the next generation console. And like, what I realize is that I've been living the dream by working on Bazite and helping move that forward. Like, we talked about the idea of Steam machines 10 years ago, and now it's 2025, and they're here. You have Bazite, you can run it on anything. And I think the convergence aspect of it is just such a hugely awesome thing. So I'm not gonna steal Bazite's thunder, but I just wanna shout them out that it's such a great project.
UCore, I guess to talk about. So the idea here was simply to make the home server a little bit easier to use. And so we've got a few different variants that we publish, some very light ones that have almost no opinionated add-ons other than driver support for NVIDIA or ZFS, but then progressively getting a little heavier with like NAS storage tools added, and then also virtualization stack added in. I think the thing that I want to make sure I communicate about is it is still trying to be Core OS, and Core OS, the whole mission is to be container-centric. So my idea there was I really want that to provide people an opportunity to learn the tools, to be engaged in container development, running containers, and so that project still is very focused on that.
And the last experience is your custom experience. What you decide to build with these tools is the important thing. And the truth is, and Benjamin will attest to this as well, is that I run a custom image of Bazite because I'm more than just one thing. I am not just a gamer, I am also a developer / sysadmin, and the good ideas that are coming from the Bluefin project and the Aurora project in particular are very appealing to me because out of the box, they're a great experience to be able to start getting working. And so the ability for me to be able to use our tooling to be able to create an experience that is completely appealing to me, I think is what's so powerful about this model and why it's so valuable. I don't want to reinvent the wheel. I remember when I first joined the project and I kind of wanted to do that. I was like, man, I want to dig into the Bazite container file and want to understand everything that it's doing and want to know what's going on with it. And it's like, that's cool. And I learned a lot by doing that. And I think we're all tinkerers in this room and that's how we function. But the truth is like, man, I've got kids at home. I've got pets. I got family. I got stuff. I got work that I need to do. Like, I just want to get up and going, and I think for you in particular, it's the same way,
Yeah, we, actually Noel and I worked together to get our image template repo put together, which we were talking to people in our community about this. Hey, it's easy to make a custom image. You just extend it. It's just a Docker file. You just do from, and we talked about how do we encourage people to learn the tooling, and this was what we came up with eventually. Just an example-based repo to demonstrate how it's done. But yes, I don't think we are naive enough to think that we're ever going to build like the perfect experience, whether it's Bazite's gaming experience or Bluefin's developer experience. Everybody's unique, and they're going to want something slightly different. And we're hoping to be 90% there. But
Yep.
if you're not, and you really do want to do the tinkering, we want that to be an option. So that's what this is, and we're going to try the demo.
Yeah, I think so. We'll talk a little bit about what it takes to build your own experience, but then we will move into the demo. And you know, live demos are always fun. We'll see what happens. So I want to talk a little bit about, though, that we've talked about this model, and I actually had a conversation right before this presentation, and you always get some of the best ideas and things when you're talking to folks, you know, right before you go on stage. And I think the truth is like, you can consume this model at any point in this funnel. It does not have to be our images. It doesn't have to be our end user experiences. It can be the upstream Bootsy based images, and like the other conversations that are happening upstream in the community are, how can I make this even smaller? Like, there's these things that I don't want, like I want them out of here. And Fedora is working on how they are going to conceptualize that and conceive that. And I think it's really, really fascinating to think about, like, IoT is, you know, they want the minimalist amount of stuff. So are they just gonna build from a scratch container? Well, that is an option because it's cloud native. That's the way that you can do things. And so, like, we were talking about the idea that it's almost like an hourglass, because when you start realizing, like, the changes that you're making to your custom changes, they expand out again. So it's kind of like this, yeah, it's a funnel, but it also kind of goes like this because of all the things that you're doing. At a basic level, and this is a large matrix of images because Bazzite supports a lot of different images, is you build the image with GitHub Actions. And then you build the ISOs with GitHub Actions too. And there's two different ways to do it currently. We're still working with upstream to be able to completely have all the features that we need, but that's the point. We're a trailblazing project, and we create things that we need out of necessity, and we want to get those things upstream so that we, you know, can continue to work on those things together. And so building the ISOs in GitHub, we serve them from Cloudflare, we upload them there, and there you go. So now it's time for the demo.
Sorry, I jumped ahead.
No, it's all good. So where we start is we have a github.com uBlueOS image template repo. And the idea of this is basically a template inside of GitHub that I can just say, I'm going to use this template. I'm going to say, okay, I'm going to create my new repo. And I'm going to be like, what if I just, you know, say I want Pizzazite instead? And I'm like, man, this thing has trains in it now. And then you'll get that joke in just a second. And so I created Pizzazite or Pizzazite. And the thing is that we're very focused on making sure that we do things correct in the community and making sure that we follow best practices. And one of those practices is signing our containers. Having a chain of trust that says, I made this thing, this is mine, and whoever wants to base off of this knows that this was created by me. And so you'll see, you know, that the initial build will fail, but realistically, the only thing you have to do, we got good documentation here, is you need to create a signing secret using a cosign key. That's how we sign all of our container images and say this is what we want. So what I am going to go ahead and do is I created my Pizzazite image. And so I'm going to go ahead and go to my terminal here. I also have another one called Velociraptor in case this goes sideways, but you know, let's just keep it in mind here. So let's just clone it down. Cool, good. So now I'm going to go in here, I'm going to go into the Pizzazite repo, and I had it copied, and then of course, you know, I go ahead and scroll down a little bit, and I'm just going to use cosign. Come on, behave now. Not in front of everybody. And I'm going to go ahead and generate a key pair. I'm not going to put a password in here because we're just going to, and we also say in the documentation don't. And essentially I've got a public key now and a private key. And so the private key needs to be in the GitHub builders in order to be able to consume that. And I need the public key to say, you know, this is how you verify that this is what was actually created. So what I will do is go ahead and implement a signing secret. And of course, you can follow the GUI if you would like to be able to create this, but for the sake of the demo and time, I'm just gonna go ahead and import that. Very cool, Pizzazite now has a cosign key. Now what I'm gonna do is I'm gonna go ahead and open this in VS Code. I'm gonna make this bigger, maybe not that big. Look good, everybody? Everybody can see? Good. All right. So I'm going to go in this build sh. Actually, no. I'm going to start with the container file. And this is starting with Silverblue main. And so the things that it's describing in here are basically other possible base images that you can use. So the idea here is essentially, you know, we have Bazzite stable in here. We have Bluefin NVIDIA. We have, you know, basically our upstream images, which are Fedora boot C as well as CentOS boot C. You can start from any place you want. But I decided I'm going to make Pizzazite, so that's the image that I'm going to start from. So I'm going to go ahead and say Bazzite stable. I'm going to go ahead and save that. Then I was like, yeah, I like trains. So let's do a DNF install SL. We also got tmux in there too. I mean, I don't remember if we shipped tmux, but you know, it's not going to hurt anything being there. As far as I know anyway. And let's go ahead and use my favorite Git tool, management tool. Go ahead and just commit this and say, I like trains, and push. So what's going to happen is I've started building my custom image. And if I go back to my Pizzazite repo, you'll see that I like trains. Cool. Go to the action. Look, I told you I'm not very good at Git. I mean, messages, you know, there's something. So you'll see that we're starting to build an image. Oh, it's crabby because I did Pizzazite, or, well, we'll see what happens here. But it's going ahead and pulling our source image here, so you can see that it's actually, I'm going to make this bigger so you can actually see it. So you can see that it is pulling the Bazzite stable image here. This is going to take a few minutes. Bazzite's kind of big, so, you know, we'll just kind of move on to another section to come back, but we'll see what happens when it builds. But there's a set of steps you can see in the GitHub workflow, and you can change these. I've even changed them on occasion. And it's going to go ahead and log into the container registry. It's going to push the image, and then with this change, basically this is how the iterative development works, where if you're familiar with container registries, cool, I just made my change. I'm just going to go ahead and pull that down and check it to see if it actually happened, and there you go. So you can develop it either inside of a container, or you can do it on a VM if you have specific GUI changes and that sort of thing that you need to do. And so that's really how simple it is to get started if you're familiar with cloud native. And if you're learning, I think that's what's so valuable and key, is that this is the iterative development process that is done when you're building containers and building applications. So I'm going to go ahead and go back to the presentation for a minute. And we're going to start talking about how you contribute. Do you have a question? Yeah, why don't we get you the, exactly.
What is it that I can do with that container when I'm done with it? Like, some things I do are code spaces, some things I might want to do are a VM, some things I might want to do is just boot it up, have it like as a boot image, live disk image or something like that.
Mm-hmm.
What are some of the things I can do with the assets that come out of that default build?
Yeah, so the result of that build, when it's done, we can show, is whatever that image, it'll be Pizzazite,
Yes.
is going to be published in a GHCR, so GitHub's container registry, and it'll be immediately available to Podman run or Docker run if you just wanted to immediately run inside that container context and see what's going on in it. In that kind of a runtime, you're not going to run your own kernel, obviously. You're not going to run systemd, but you'd be able to inspect the contents. You could use bootc, as we talked about earlier. Bootc has a bootc install, and you could just splat it to a disk, and you could then boot off it. If you're really confident, because you've read all the docs and you know what you're doing, you could rebase if you wanted, because you've been running Bazite, and now, oh, I just made this small change, and so I'm going to switch over to my custom image. You could do that live on your machine, but
Yep.
probably do it in a VM first, just to be confident.
Yep.
Yeah,
Yeah, absolutely.
I should
With
say
Bazite before?
bootc switch.
Bootsy switch.
Bootsy
Yes, that's
switch,
a better
but
way
even
of putting it.
that, but then from then on, I'm diverged, right? So like I won't
Yep.
keep picking, I'd have to keep pulling your new, rebuilding and pulling in to keep
Correct.
my patch in that rebase.
Yes, you would, well, no, what you would end up doing is, because this is stored inside of GHCR registry, you would basically want to create, which is a cron job that's already created, you would essentially rebuild that image on a regular basis so that you can stay up to date with what it is that Bazite's doing, as well as the packages that you're doing on top of that as well, or any changes that you're making. So it allows you to basically always stay in sync with your upstream. Yep.
So if you're doing image signing with a key, and if I'm building my own image with my own key, I remember one of the problems with CoreOS, the original CoreOS prior to Red Hat, was you could theoretically make your own fork of CoreOS just like this, but you would have to reformat any system you wanted to install it on, because the existing system wouldn't recognize your key and therefore wouldn't approve your image to be applied and updated to. Is there a way around that, or are you essentially kind of in that situation here as well?
So the policy that we have on the container, let's see, it's like Etsy containers policy.json. Within the Universal Blue environment, we only trust our own key if you're trying to pull an image that matches our organization. But if it's a key, or sorry, if it's an image that's from your personal registry address, then there's not, the default policy doesn't enforce the key. So it would complain if it was an invalid key, but it won't require it to be signed in the first place. So I don't know if that.
Can I add my own key to be trusted then?
Yeah,
Yes.
you can modify the policy yourself.
Yes, absolutely. Yep.
That would be like an advanced addition to the custom build.
Yes, exactly.
Or
yeah.
a manual mod.
And if there's needs there too, I mean, it's a open project, and create an issue or even a PR, and since we're talking about contribution, and if we can find ways in which to be able to make that onboarding easier, for sure. I mean, that's definitely a need there.
More of a comment than a question, but the Bootsy image builder action that we use will also spit out other cloud images, so you can grab a UCore with NVIDIA, spit out AWS images, and go to town.
Yep. And we also intend to upstream that action as well, which will make that even easier going forward. Yes?
Can we see your VS Code pets?
My VS Code what?
Pets. You had the VS Code
Pets?
pets extension.
I'll show you in a little bit if we have some time.
Yay.
That is important, though. I 100% agree. So let's talk about contributing. Oh, one more. All right. All right.
That's fine.
Yes, yes, absolutely.
Oh, hey, what's up?
We do plan to do more Q&A also.
Yes,
so-
we
So by
have
the way, I'm
Q&A at
Steve.
the
I'm
end
the guy
as
who
well.
did that YouTube podcast on running Bazite and Atomic. That's what you recognize probably, right? Yeah.
Yep.
Anyway, I'm excited about this, but I'm in my head. What I care about is practical applications of like, okay, now what does that get me? And so like one of the things I do is I spin up workshops. I want to test things out on machines. Like, forget contributing. Yeah, maybe I will. But what I really want, so that I can go spread the good word, is like, show me all the cool things that you have now let me do. Because I teach machine learning. And so I want to build one of these images with all those libraries
Yep.
pre-installed, because that takes forever to download. And I want to have a couple data sets in there, because that takes forever to download. And I want to make like a custom, like, computer vision. Aurora's the best. So I'm going to pick a computer vision Aurora image, and then I want to know what I can do with that once I've built it.
Well, I'm not sure if this is the answer, but I've been using Linux since Slackware in like 1996, okay? So I've not completely been on the desktop that long, or all continuously, but off and on. And over the years, I mean, it went from like just this passion for reinstalling and tweaking and finding ways to automate those kinds of builds to eventually I reached the point where I was like, oh man, I have 3 kids and a wife, and I have like 6 machines in the house, and it's literal work. It's like that was the joke about being tech support for a family of 5. It's work to maintain systems, whether it's 5 for your family or for a lab.
Yeah.
And so that was what really excited me about this project is I can, and this is before we had a template that even made it easy, right? But it's like, it's a container file, it's a list of, I'm using this already established good platform that did most of what I wanted anyway. And now it's like I've got 15 things I need to do, steps I need to add to a container file, and it's gonna run every day or whatever your schedule is, and it'll be updated, and we have an auto update too. So, I mean.
Yep. And I think, like, for me personally, like, what does this get me? What I explained, which is that, you know, I'm not just a gamer, I'm also a developer and sysadmin, and including those tools into my image for Bazite gets me 90% of the way there. And so I just steal the best practices from other ways of doing things, and even from Sherman's images I've stolen stuff from too. I mean, maybe not stealing, but borrowed is a better term for that. But I think the truth is that the sky is the limit with it. And your point of AI, we are actually working on that. You know, Bluefin is working on an image that is specifically focused around AI. And I'm sure Aurora is going to follow suit as well because of the demand and desire for that, you know. But I think the truth of the matter is that we are looking at what are those other experiences and things that we can do. And educating the next generation is definitely one of those things. And any help that anyone in this room can provide to do that as a contribution is hugely valuable.
What's the most out there use case you can think? Okay, so what's the most out there use case you can think of? Sorry. No. I want you to like.
Out there
Yeah,
use
you
case.
can answer it.
Yeah. Anything you can think of. Anything you shoved in a Docker file, you could shove, except it's the OS. You could make a robot. We made an AI workstation. You know how you go somewhere, it's like run the script and everything gets perfect. You do it in the container file, it always comes out perfect every single time. You could do classrooms, labs, however, we can also add in container workloads as part of the life cycle. So in Etsy, you can put in a quadlet that says, I want these service units to come here so that when it comes up, you have a life cycle bound container that will do the Docker pull in the background using all the policies that you want. So your students can have a workstation, but also it's running Kubernetes or whatever other stuff on there, and it's on there.
Could I deploy these images in like Kubernetes, right? Is that the other thing? Like, could I use this as a base image for a pod?
In theory, yeah.
You can.
I mean, KubeVirt.
Okay, so UCore is
Yep.
the one without all the GUI stuff. Is that basically, like,
Right.
I would want to do this off of UCore?
Yep.
Okay.
Yep.
Yep. So if you're like,
KubeVirt,
I want the exact
Kubernetes.
Kubernetes node, but I have to have that agent from your work that's some janky RPM or whatever that isn't going to fit anywhere, you like shove it in there. Any of you need to Stig servers to get them all up and running so that your compliance stuff, just shove all that stuff in a container. All that great stuff, and yeah, sure, dude, a 30 gig app or ISO comes out, whatever, blast the disk. You just DD the disk.
Absolutely.
Does this answer your question?
It's the U-base image? Is that UCore? That's
Yeah,
the one I think
UCore.
for, like,
Yep. It's the Core OS based image, exactly.
So are you aware of anybody trying to use this for edge deployments where you need to deploy both an OS and some sort of configured managed OS?
Not yet, but Steve, you know I'm working on that. Drones, like we can do it all. It's one model for everything.
Right. That's the whole point. Remember what I said?
It's just a Docker file.
Yes.
Well, I mean, isn't the Steam Deck an edge device?
Sure.
I got your edge device
Yeah.
right here.
Yeah. Right. We're proving the edge use case. I mean, that's
When I get containers for that chip architecture, like I'm working with Qualcomm now as well.
drivers. Put the drivers in the image.
So,
Like,
No, drivers in the image. If you go to the show floor right now, there's a ARM workstation you can check out right now running this exact same tech.
you can let me talk, Kyle.
do you have a question, Kyle, or are you just heckling? All right. Let's talk about contribution.
Oh, wait. Question.
Question? Oh, geez. Okay, yes.
Hopefully this will be a quick one. So you're talking about using this for desktop use using FlatHub. Honestly, I've occasionally had problems with things in FlatHub where, like, if it needs to call out to something in the shell, because of the way FlatHub isolates the application, it can't do that even though that's right there in my path. If I need to install things from RPMs or if I need to just shove a binary in there somewhere, like how is persistence of those things handled? Do I need to do that upstream in my image build, or is there a way for me to just do that on my local system and have it persist?
That is the best practice, is that you want to include those RPMs and tooling inside of your image. You're doing day 0 operations that you sometimes do in day 1 and day 2. That's the desire there. And I really love that, actually, for me personally. It really helps just simplify things in the sense that it's like, I just want something that's out of the box. As far as like, if you need to test something or run something, we have tooling which we use from upstream called DistroBox, which basically can run RPMs and other tooling, even Debian packages. I mean, if you love Ubuntu, I mean, go crazy. Like, DistroBox is one of those Swiss Army knife tools that it's like, if you're a power user, and again, you're sliding into that, 10% category of like, I just need to do this thing, DistroBox is a tool that we allow you to be able to use to be able to integrate with your home directory, able to install packages. I mean, I run DaVinci Resolve inside of DistroBox because there's no, easy way to do it with an RPM. Like, I could do all that work upstream, but like, we have community members that have been able to contribute those types of things. So again, it's kind of one of those things that ideally for me personally, I'd rather have DaVinci Resolve in a flat pack. That's where I'm trying to aim people to go, is create a flat pack and make that simpler. But the truth of the matter is that yes, it's just learning different ways of doing things that are, like I said, fully valid and fully viable. Yeah. Yeah. I mean, the truth is, though, too, is that that's the whole point of containers, is that it makes that experience. I don't like polluting my system either. I like a stable, rock-solid system to work off of, and if I'm doing anything that I know might blow up my system, I would prefer to do that in a container, because the worst-case scenario, I remake that container, and cool, we're good to go. So I really agree with that methodology and that idea. So, any more questions, comments, thoughts before I move into contribution section? And I'll also I promise you I'll come back to the demo, and we will see green, hopefully.
I think we can go quickly through contribution.
Yeah, contribution's pretty quick. Yeah, absolutely. So, if you see something, say something. That's really all there is to it. We are trying to build our community on platforms that are accessible to people, and a lot of us are on GitHub, but also some of the issues that we've seen have also been proposed in our Discord server or proposed to me just directly, like, see something, say something. That is a way to contribute to the project, because you're saying, I have a problem and I want to be able to use your software, I want it to be successful, let's get that solved.
Yeah, I mean, proposals are always useful. There's kind of a general open source contribution. I've noticed that a lot of folks will show up and maybe drop a huge PR. And sometimes, I mean, it's good, or the intent's really good, or the feature's really good, but it's just done in a way that's not really gonna mesh with what we've built already, because the person came in and just wasn't part of the team, or never took the time to get involved in the community first, or look for some of the low-hanging fruit that are out there. Do we have that phrase somewhere, low-hanging fruit?
Yeah. I mean, good first issue.
We do try to have issues in our bug trackers for good first issue.
Yep.
To try to get good contributions, but
or just general needs that we have,
yeah, documentation is always helpful. We've had somebody contribute a lot of documentation that was just wonderful.
Documentation is the most important thing for your project, because if no one knows how to use it, no one's gonna care. I'm sorry. That's just the reality of it. Pull requests, like we talked about, is getting your changes in Universal Blue. We use GitHub. It's kind of what runs the world. Upstream work is another way that you can contribute. And we try to do this all the time. What I was saying about developers adding their stuff to FlatHub, please. Because there's a dream of mine where we don't have to think about the esoteric use cases where it's like, oh, I gotta run this thing in a distro box, or I have to layer this thing in my custom image or anything else. Like, it would be ideal to be able to have those things already just as a Flatpak, consumable, useful, that sort of thing. And we need your help. That's the truth of it here, is that we want to focus on the user experience and grow the Linux desktop. We're targeting those 90% of users. You know, like
94, right?
94, that's true, because Linux is 6% of the desktop market. So it's really one of those things where we want to target the 94% of users that are using this thing in their pocket, their phone. We want to target folks that are using, you know, just a web browser on their machine or playing video games, which is why it's something that's been growing. And we want to focus on the next generation, you know. That's just the truth of it. I want to give a special thanks to all of the people that have contributed over the years to this project and the teams that have been involved to really make this vision a reality. I just can't thank them enough for all of the things that they do day to day in order to be able to make this better. And also I want to thank all of you for being here and giving a crap about this stuff, because it's important. And that's just something that is so dear to me. So if you want to learn more about our project, you can go ahead and scan this QR code here. It will take you to the Universal Blue website. It's kind of our nexus where it will take you to all the different places that you need to go. And I'm not exactly sure how much time we have, but we may have a little bit more time for Q&A. So we've got 5 minutes. So anything that's on your mind, just, you know.
Oh, no. Well, I'll hit you on one. Gwen
Okay.
says no, but I'll cheat. If I wanted to reprovision an out of maintenance old Chromebook to run this, is that viable, doable, or?
What a great question. We've actually got folks in the audience that work on this stuff and know more about Chromebooks than I'd ever.
I do have a Chromebook
Think
running
about
it.
If you
But
want to
yes.
hear about Chromebooks and Linux generally, please come talk to us. We're the Fira Terra people. Please, we'll talk about Chromebooks all day.
Yep. But also, yes, if it runs an x86 processor,
Wanna hit the-
we're good. What's that?
You said you were going to show
Oh,
something.
crap. You know what? We got to go back to the demo. Oh, no. What happened?
It
What'd
failed.
you do? That's what live demos are all about, everybody. Oh, it's GitHub. Yeah, it's GitHub. But I will show you Velociraptor, which is a new project George's not even aware of, where I add a SL package, because that is clearly missing from Bluefin. So is it a hard fork? Oh yeah. No, we rely on Bluefin over here at Velociraptor, and we're very proud, really proud to have them as being our upstream. But as you can see, I changed it to Bluefin stable. If I go back over here to the build, you'll see that I added the SL package. And if I go to the action itself, you'll see that everything is green, because I did this in the hotel room, preparing for this moment. So as you can see, it went through all the steps and succeeded, and I can consume this image. So. I want stickers. Where are my stickers, George?
You can help hand out stickers.
Oh, nice. Thank you, everybody, for coming. Very much appreciate it.
Oh, here's a question.
One more question. Go and ask.
Yeah, where do I look if I want to export this to like an AMI or something like that? You guys mentioned you can splat it on a disk. That's like not super useful for like provisioning infrastructure.
Right.
I saw your pipeline exports to an ISO. Am I on my own from there, or like
Right.
how do I?
So right now, we don't have anything in our pipeline that's doing that. There was a mention about Bootsy Image Builder, which is it's upstream, right?
Yeah, we're
We have
working on an
a-
action to move
we have
that
an action.
upstream to make that a lot simpler. And so if you look at any of the custom images like Bazite and stuff like that, I mean, we do have an open issue actually about adding ISOs as a thing
hold
to
on.
the image template,
But Bootsy
again,
Image Builder has the ability to generate
Yes.
the AWS AMIs,
Yeah.
stuff like that. So that's where we need to go. We don't have that in our toolkit today. That we're not providing it.
Yep.
Yeah.
Yeah. Yep.
Yeah, and that is something that I really want to get into UCore, by the way. So
Yep. Absolutely. All right. Yep. Yeah.
Okay,
Yes.
please join me in giving a round of applause to Benjamin and Noel for this great presentation.
Thank you very much. Come to the Bazite talk at 5 o'clock, room 105. Be there or be square or something. I don't know.
Testing. Yep. And this clips on your belt, so you're live now, but if you want to, you should just be able to move the microphone up and down.
Testing. Can everyone hear me? So I should have to wait till. Can everyone hear me? So just waiting for the exact time to reach 15:45, 3:45. So 3 minutes more.
The way these talks are recorded is they're just like one continuous recording, and so without the timestamps, it becomes just difficult to find your way. Also, like, this is all live right now, so I can't start telling jokes or anything because it would just all show up on there and look terrible. Just no. Oh, someone laughed. Yes. All right, we are ready to start our next talk. I'm super excited to introduce Divine. He is going to talk to us about all these cloud native technologies, and I'm really excited to hear this talk. So please welcome him to SCaLE.
Can everyone hear me? Hi. So I'm excited to be in SCaLE. This is my second SCaLE, right? My name is Divine Odaze. We will be speaking about cloud-native technologies, the building blocks of modern database software. So this talk is one of the last remnants of my time at Several9. Several9 is a database company that creates database automation tool, right, like cluster control that's used by enterprises like Visa, Kezia Permanente, and several companies mostly based in Europe, right? It's a Swedish company. So I'm no longer a technology evangelist there, but yeah, this talk, I applied it when I was still there, and I gave it in London last year, and it's great to see that it's accepted here, right? I'm a database on Kubernetes ambassador, so this talk is to promote a user interface, right? A seamless user interface or a seamless internal development portal for your end users, right? An IDP, a UI, or a portal using Backstage, for example, right? Or Clutch, or some other tooling, right? So it's possible to do that, right? But then again, still some organizations can't actually invest the amount of time to build everything from the scratch, right? Using this open source tooling. There we talk about using off-the-shelf solutions and stuff like that. So in order to like contribute to the ecosystem, right? So at the several nights we worked on I think 17,000 word white paper on how to think about designing your DBAS, right? Because we've built DBASs, right, for organizations, and we built DBAS that organizations use, right? So how to design architecture and design considerations, right? Or an operational requirement in building a DBAS. So from day 2, which is like requirement architecture design, day 0 rather, to day 1, which is install and setup and configuration, which ChatGPT can do for us. Don't mind me, I'm joking. But yeah, then to day 2, right, keeping the lights on and maintenance and stuff like that. Then the end, maybe maybe you're out of business, right, and you want to shut everything down, then you can just delete the entire infrastructure. Or maybe you get a buyout or something, right, and you have to use the internal DBAS of the company that buys you out and stuff like that, right? So you can scan this QR code and you can read the white paper. It's actually an interesting read. It was based off on DAPA, right? And I'm also giving a talk in London in a few weeks, right? So if you're in the UK and you'll be in London, at SRE Day London, yeah? So I'm giving a talk on designing, just going in depth into this white paper, right, to talk about designing a DBAS with DAPA. So yeah, so this is an interesting read and I hope you enjoy it. And if you see any error or anything you like to question, like everyone is always open to learn, right? And I'm open to learn and the entire team is open to learn. So, sorry, okay, if you're still scanning it, I'll put it back. Okay. Don't worry, we have time, we have 1 hour, so yeah. So, yeah. Okay, I see most people have scanned it. I hope the code actually works. It works, right? Oh, thank God. So, yeah. So who built a DBAS with Kubernetes, right? So these are popular companies, right? Zolando, which gave us the Zolando Postgres operator, which I'll say is one of the initial operators in the database on Kubernetes space, right, for Postgres. And then we have Shopify that build their own DBAS system, right? So yeah, like I said, these are big companies. They have the budget, they have the money, and they have the time, right, to build that, right? Then talk about, that's why emphasis on being interdependent, right? Using tooling that already exists, but with the mindset of having control, right? Not using a tooling that you'll be locked in and you'll have to pay so much amount of money because your team is dependent on that, right? So Kubernetes, we don't need, if it was 10 years ago or 5 years ago, right, we would have to preach Kubernetes, but now we don't preach Kubernetes anymore. So yeah, so Kubernetes is here and is here to stay, and hopefully my microwave in the future, as someone told me, right, would have Kubernetes inside. So maybe as I eat the food, I learn more Kubernetes and stuff. So don't mind me, I'm making silly jokes. So yeah, but then again, right, not everyone wants to put their data on Kubernetes, right? I've spoken with, I think, hundreds of people, right? And I think it's like a tug of war, right? One side, oh, pro Kubernetes, put data or their operators and stuff. The other side, data, Kubernetes, no. And I was speaking with someone that works with some of the banks in the UK, right? Lloyd's Bank and stuff, right? And he's mostly in, banking environment is highly regulated, right? So he said that he can't even listen to what I'm saying. He can't even listen to conversations around that. Yes, it's possible, but adoption, right, of that. So, but then again, but aside from putting the data on Kubernetes, right, another idea that we've worked at, right, at several nights, and also a lot of companies have been doing is building a DBAS, mainly not on Kubernetes, but with Kubernetes, right? So that brings me to the next aspect of the talk, which I think is the final aspect, right? So when we say building a DBaaS with Kubernetes, right, we mean using Kubernetes as a control plane, right? And to manage data on VMs, which we all love, right? The VMware, I don't know if you love VMware, but yeah. So where the database themselves aren't directly deployed on Kubernetes, right? So there are several ways to use Kubernetes to deploy and manage your database infrastructure. So like I said, right, at several nights, like we built a software called CCX, right, for CFPs, which helped CSPs rather, so the CSPs being cloud service providers, right, most especially in Europe, that want to offer DBaaS, right, that want to offer DBaaS to their customers, right, but are not at the scale of the likes of AWS, not at the scale of Azure or DigitalOcean, to be able to commit that much resources in designing and maintaining a DBaaS, right, at scale. So, in a nutshell, right, CCX is a drop-in DBaaS, drop-in in the sense that a CSP can white label and offer their own front end, right? So, and also get that high SLA, which everyone loves, because you need high SLA for your database, and they build with the already existing infrastructure, right? And the control plane is deployed on Kubernetes. But then again, most companies, they use OpenStack, right? They have their VMs, or they also use AWS, right? And use EC2 instance. So you use Kubernetes to manage and control database on VMs and other infrastructure. So I'll just wait till everyone takes picture of the slides. So, and there you can see some marketing related info, right? 24/7, high SLA and all that. Then the architecture. So basically, as I've already mentioned, right, so CCX deployed on Kubernetes, and with all using already existing, being interdependent, right, already existing software. So there you have the MySQL operator, right, for that helps in managing the metadata of the deployment, right. You also uses the PostgreSQL operator, right, to manage the control plane data. And then you have other services. But the major thing about this, right, and being the goal, which is to avoid lock-in, right. The major thing about it is the fact that you can take out any service you want, right? Any tool. Let's say you no longer want to, let me look at the architecture. Maybe you no longer want to use external DNS, right? You want to use a different DNS service, right? You no longer want to use Grafana, or you no longer want to use Victoria Metrics. You can take it out and slot in your own, right, as a CSP or as a company building an internal DBaaS, right, and deploy on Kubernetes. Then you also meet the needs of your DBAs or your team that don't want to be on Kubernetes, right? Or don't want to touch Kubernetes with the football. So you can also deploy on AWS, like your VMs being deployed on AWS, right? On Google Cloud, on OpenStack. We did a talk, a partnership with a service provider in Asia, in Indonesia, right? So, but we gave a talk at Open Infrastructure in Japan, same last year, and we talked about how it integrates with OpenStack and all, right? And you get your vanilla databases, right? The database you love, MySQL, Postgres, and all that, right? And also is there S3 compatibility, thinking about from a backup perspective and all, right? And also provides like different interfaces, right? DevOps teams and teams, we want to use Terraform, or maybe OpenTofu. If you're against Terraform now, they change their license. And yeah, and also an API, right? Being API centric, I think is the way to go, right? Everyone runs away from SSH. I know you run away from SSH, right? But being API centric, want to make API calls and stuff like that, right? And you get any way you want to interface with your developers and your users, right? Your end users want to interface with the technology. So moving on to the installation step, right, is just divided into 3 steps. So you deploy the dependencies, right, on Kubernetes and its core services, right. It's based on still the idea of being a loosely coupled architecture in the sense that you must not, there is like a default quick start, right. There is a default configuration, but then again, you can take out whatever you don't want, right, and put what you need, right, and like some of your internal tooling, or maybe you have like a different metrics provider, or you're using something else in your organization, right? So hence it being divided into like 3 different aspects, right? So the documentation, you can Google it and check on GitHub and read through the 100 lines of Helm charts, right, and experiment on that, and that should be fun. Yeah, it's fun. So yeah. So who built DBAS with CCX? So I've already talked about that. So mostly in Europe, right? Because that's where everyone is pro data sovereignty and everyone is fighting against someone having control of their data and stuff like that, right? But yeah, it's a need, right? So this is a Swedish cloud provider, and the other one I talked about, Lintasatra, who deployed database on the control plane on Kubernetes, then use OpenStack for the data plane, right, which is the data layer. And yeah, and they currently have thousands of users around the Nordics region, right, and also from other parts of Eastern and Western Europe. And that's bringing me towards the end of my talk. And then the next slide, does this make the role of a traditional DBA defunct? I don't know, can anyone like give me their opinion? Exactly, right? So absolutely not. I don't know. Was that fun? Did I try? Yeah. So yeah. So absolutely not, right? So because why this question is because I hear this question a lot, and I actually gave a talk at the DBA Data on Kubernetes community last month about this very topic, right? And if you go on Reddit, I don't know anyone here that lives in Reddit. I kind of live in Reddit. I don't know why, but Reddit threads, you see a lot of like Kubernetes people saying, we don't need DBAs any longer, or executives that have watched like quite an interesting talk that say, that means we can actually lay off a few DBAs and stuff like that, right? So as it said, right, there's more to databases than just deployment, right? So you can't replace like that skill, right? And I've read a lot of like articles. I should have put them in my slides, some things to scan, right? Of like that buttress that point, right? And you can Google my talk, which is DBAs, like are DBAs no longer existent, right? Or you check the Data on Kubernetes community, YouTube, and you see like so many resources on that, right? So DBA is like, I'm not a DBA, but I've worked with a lot of DBAs, right? And every time I respect them more as things happen, right? Because like that, it's a skill and it's something that is learned over time, right? So all the hype with operators, the world is going to change, there's no DBAs, AI, and stuff like that, right? Obviously, we want people to do less work. So what I've seen, right, and talking with DBAs, I'm going to give a talk with an Oracle DBA in a few months, right? And he has been experimenting with Kubernetes, right? He is welcome to Kubernetes, then that brings us to the next step. It's all about, software is always changing, right? It's all about improving and learning about like how to manage the data on Kubernetes. So the DBA's skill, maybe we know that job descriptions will always change, right? And you will may no longer see a DBA, a database administrator, right? Like that. But then again, those skills, right, of being updated on the new technologies and how to manage data on Kubernetes is essential. So yeah. This is the end of my talk. Wrapping up, the journey of database deployment is far from over. I don't know, maybe some of us will live 100, but maybe we can see so much more changes. Cloud native technologies, particularly Kubernetes, they are powerful tools for managing stateful workloads like databases. If you're interested in a drop-in DBAS solution, you can scan that QR code to learn more, aside from the resources brought. So, yeah, thank you all for listening to me. And I don't know if you know Eddie Wasef. I think he was at SCaLE last year or 2 years ago, right? So we had a podcast. We talked about database on Kubernetes. I think he was at Vonage, but now he's at JP Morgan. So it was an interesting conversation. So you can just take a picture of that and you can Google the podcast and you can listen to people talk about Kubernetes and data and stuff, right? And make arguments and all fun and all. We know we're software engineers. I write Java. Someone told me a few hours ago, Java? I hate you, just like Solomon said. So thank you all for listening to me, and I don't know if anyone have any questions. So if you have no questions, thank you all, and do have a great rest of the conference, and enjoy sunny Pasadena, and hope the rain doesn't fall again.
Hello. Can you hear me?
Thank you. Do you need an introduction? Would you like an introduction?
Sure. That'll be great, yeah.
Yeah, we can hear you. And then here are the 10-minute warnings, the talks from 5 to 6. 5 to 6. And so it's 10 till, like, if you still, how long is your talk?
Probably about like 40 minutes, and then I want to leave 20
so
minutes.
It won't really be necessary.
So just keep that handy, but I think it won't be like just in case Q&A runs over, but I think like if there is anything, yeah, that's about it.
Yeah.
All throughout as well, but I want to leave some time for like questions for people at the end as well. So you don't mind being in the, okay. Because that's a more conversation rather than me going on a monologue. Can you all hear me properly? Okay, thank you.
Hello.
Thank you so much.
Yeah. 2 more minutes, yeah. Kiran Golu. Yeah.
Hello, everyone. I'd like to introduce Kiran Golu, and he would like to keep this session conversational. So please, if you have questions, raise your hand, and I'll bring the mic around, and he doesn't mind interruptions at all. So thank you.
Yeah, thank you. Hi, I'm Kiran Golu. Today, I would like to talk about fast and cheap observability. You can have the cake and then eat it too. More often than not, you have to choose between speed, cost. What if you can have both is the purpose of the talk. And before we get started, I would like to just give a brief call out for International Women's Day. Thanks to kind of like all the incredible women has kind of like who's moving things forward. So yeah. What I will talk about today, the key challenges with the current observability tools and how are we addressing them today, and the key shifts that are kind of like defining the future. And we're also going to talk about the new architectural first principle approach that is like faster and cheaper, and some of the results that were achieved, and what organizations need to do to stay ahead. A little bit about me, co-founder and CEO of like Bootable, an observability startup. Before that, like I used to run platform engineering, cloud platform engineering at like Rubrik while we were scaling to almost like $500 million in revenue. And before that, founder of an incident automation startup backed by Y Combinator. And in the early days, I was a founding team member at like Amazon S3 and DynamoDB. For the most part of my life, I spent like a lot of my time on the building developer products, scaling them. So before we dive in, what is observability, right? The definition of observability is like what's happening inside a system by looking at its outputs. So you can look at like logs, metrics, and traces, and each of these signals serve a specific purpose. The core idea is like the observability goes beyond basic monitoring, helping engineers quickly spot issues and figure out the why behind why the issues are happening. Here is a typical observability stack. You have a data collection layer, which is happening via agent, API, and so on. And then you also have different data collection tools like OpenTelemetry, Prometheus, FluentBid, eBPF that are shipping your metrics, logs, and traces via a data pipeline to a data storage layer. And the data storage layer typically has like a hot tier and a cold tier. And if you look at like hot tier, like it's usually expensive SSD based. And you also have like a cold tier, which is like more of an archival tier that is stored in like S3 or some sort of like an object storage, Azure Blob Storage or Google Cloud Storage. And then you have a third pillar, which is like data visualization layer, which is provided by Grafana, like Elastic or Datadog or Persis and tools like that. We're going to reference all of these elements in the rest of the presentation. That's why I wanted to give a brief overview here. So legacy observability tools are broken, right? Like the key reasons why they're broken is like one, they're too slow, and two, they're too complicated, and three, they're too expensive. So what changed? So the key drivers behind this are like one, we are switching to kind of like cloud native and AI workloads. And there's an explosion of data and microservices that is making these systems extremely complicated. And it's also a big line item. If you look at the overall observability spend, it's actually a third line item in the overall engineering spend. First line item is the people cost, the second line item is the cloud infrastructure cost, and the third line item is like your observability cost, and it's growing faster than your cloud infrastructure spend. So what? So how does it impact kind of like various teams and various players by having these changes? So let's look at each of the players, right? Like the teams. How does it impact like SREs, site reliability engineering teams? Hey, you know what, like my application engineers kind of like don't care about kind of like breaking production. I'm responsible, I'm getting woken up at 2 a.m. Did any of you kind of like face that challenge? I'm sure, so this is a common problem. And by the way, like keep the session interactive. If you have any questions, feel free to kind of like raise your hand. I think we can have a conversation about that. What are some of the other things that like SRE teams have faced? It's not reliable. Like it just doesn't work. You know, scaling my open source stack, the queries are slow. Despite over provisioning, it just doesn't work. Scaling my open source stack is hard. I have to rebalance my Elastic clusters, and then still my log queries are slow. And the last one is if you're using something like commercial vendors, you have to reduce your observability to reduce your costs. Hey, you know what, like my boss asked me to kind of like reduce costs, but like my product engineers kind of like don't like me anymore because like I'm actually started to block metrics and block some logs, and they can't get to kind of like what they want. So let's look at platform engineers, right? So platform engineering teams are like, hey, there are too many dashboards, too many alerts. I can't easily figure out what my engineering teams are sending, what the different services are sending, and what we actually use. Why can't my observability system just answer my question at any cardinality? Why do I have to kind of like restrict and then do code reviews and then stop blocking some metrics and so on? Because the teams are not able to send all these things, the customer experience also sucks. So let's look at like product engineering or application engineering teams, right? So the problem with the product engineering teams is that their users or their customers are like noticing the problems before they do. And it results in kind of like bad customer experience. You know what, like PMs are constantly bugging us with questions and interruptions, product managers here. Why can't they figure it out themselves? Like if the observability tools or like these tools are like easy enough, they should be able to kind of like look at this. Hey, did the new release cause any regression? They should be able to, we just rolled out a new feature flag. Is there any challenges over there, like with the new release or like with the new set of users that we rolled out this feature to? Why can't I get answers to my questions ASAP? Whatever, like the observability system should be able to answer these questions. And I want to get in, get out as fast as possible. I don't love my observability tools. You know what, like they're designed for a purpose. My goal is to kind of like make sure that I can get back and then go back to building revenue generating features, the stuff that I like to build. If you look at like engineering leadership, right? Say, hey, you know what, like we're heading to an IPO. My CFO is asking me to kind of like reduce costs to improve my margins. These commercial tools like Datadog, like few others are like expensive, and then scaling open source tools cost too much money, too much people time, and also results in kind of like customer experience and availability challenges and outages. What should I do? How should I kind of like balance which decision I'm going to make? Why can't I scale cost effectively? Yes, I want to scale, I want to send a lot more data, but I can't scale cost effectively. We're sick of migrations. Like there are weird lock-ins. You know what, like there's a weird query language. Because of that, like we can't switch to either open source tools or we can switch between vendors. And like I personally have gone through like many such migrations, painful migrations at like Rubrik. And the last one is like, you know, no vendors today build cost attribution into the core part of the product. Why should I, as an engineering leader, like engineering team, build those features myself, or like our team should build on top of the observability tools? Why can't it be kind of like natively part of the observability stack that we currently have? If you look at product managers, using observability tools is like not intuitive at all. Like kind of, I have to constantly kind of like go back to my engineers and ask these questions. Is there any regression? How is my usage and adoption of like the features looking like? How do I measure the performance and availability of my premium customers? You know, they're constantly shouting, they're going to churn if I'm not going to take care of them. So are they happy? So these are kind of like the constant questions that are coming from all these players, and these are all kind of like real challenges. Okay, so it impacts multiple teams, we understand that. So does any of the existing tools kind of like solve this problem? Let's look at the landscape, right? Both open source and commercial tools have challenges today. If you look at like kind of like open source tools, like Prometheus, Grafana, or Elastic, commercial tools like Datadog, Dynatrace, you can name like a bunch of other observability tools as well. One, they're too slow. If you look at open source tools, they're like not reliable, and query timeouts, despite over-provisioning, and they're complicated as well, right? They're not horizontally scalable. I have to vertically scale them up, yet they're not fundamentally designed for horizontal scalability. And they break at any meaningful scale. If you look at like Prometheus, Grafana, even Elastic is known to have like a lot of operational challenges. And you need an army of engineers to kind of like manage this stack. And it's not a fun job either. All I'm doing is like managing, making sure that it's up and running. Nobody likes that. And if you look at commercial tools, the challenges are like, hey, you know what, like there are too many dashboards. Like, you know what, like How do I train my experience and like new engineers for that? And they're not optimized for kind of like end-to-end experience as well. Each piece solves a piece of the puzzle. And I have to constantly balance my budget and visibility. It's hard to do cost attribution, something that we talked about, and they have like weird lock-ins with their own proprietary language. I can't own my data. It is sent to the vendor, and the vendor can't share the data with me. Why? And we talked about it's a third highest spend in engineering. It's like quarter of your cloud bill. It's a meaningful spend. So how are different companies kind of like trying to solve the problem today, right? If you look at the first wave of companies like Datadog, New Relic, Dynatrace, AppDynamics, they tried to solve it for the user experience. They did a pretty good job. As things were moving towards the cloud, as applications were moving towards the cloud, they created a nice user experience so that there is visibility into like what's happening inside the applications. As the data kept on growing, as there is an explosion of like data and microservices, scalability became a problem, cost control became a problem, and then the new set of tools came, Prometheus, Thanos, Cortex, and Chronosphere and Cribble, which try to solve this problem for scale and like routing of data into different layers. And there is Mimir and Victoria metrics. These tools and companies are solving the problem, but like not cost effectively. So they try to solve the problem via tiered storage. There's a hot tier, there's a cold tier. Depending on that, like you have to juggle the data between these tiers. It does help though. I think they did solve the scale problem, but like what still remains is the cost efficiency. Let's get into that. So why the legacy architectures are like kind of like no longer enough for your cloud and AI workloads? The fundamental reason, as I was alluding to, is actually they are not architected for cost efficiency from day one. Instead, they are architected for scalability and experience, which are also important. And a lot of these stores are like row-based data stores, and they're not designed for high cardinality data. So what is a high cardinality data? Being able to kind of like drill down things by customer. If you're a security monitoring company, being able to look at things by camera and then see, hey, is there an increasing traffic for this particular camera, for this particular IoT device ID? Being able to spot problems, slice and dice by any granularity. If you're an e-commerce company, being able to look at things by a particular store or a store ID, and then if there is an order drop or not for that particular store, being able to distill down to that level of granularity is challenging with the row-based data stores because they use expensive and slow SSDs, and SSDs can be as expensive as 25 times more expensive than your object storage. And replication adds like more cost. And the fourth line item is actually always running compute adds to the costs. Like most of the time, if you're looking at in the weekend, 99% of the data is like never being queried. It doesn't make sense to run like a dedicated compute when you're not using. And they're all based on kind of like lift and shift on-prem architectures. So those are the challenges the current legacy architectures have. So why now is it kind of like a time to rethink? Observability has become a data problem. So there's a data explosion as we discussed. And there's a separation of compute and storage phenomena started by Snowflake. And there are like lots of innovations happening in the data warehousing space. People are creating serverless databases built completely on top of object storage. And people are creating like data streaming architectures. Kafka built on S3, some new innovations like Neon, Warp Stream. And they're leveraging like very, very cost-efficient architectures, much like what DeepSeek did for like disrupting kind of like the AI workloads for OpenAI and like Claude. Cost efficiency is the name of the game. And there's a serverless wave. There are like lots and lots of innovations happening around the amount of parallelism that you can have and the reduction in the cold start latencies. So you no longer have to wait a long time, few seconds before you spin off hundreds of thousands of Lambda functions going against your object store, returning the results as quickly as possible. And the last one is like generative AI. But you know, observability data has like different properties compared to this like analytical and other systems. You mostly care about recent data, and time series data is like highly compressible. And 95% of the data, even like more like 99% of the data is like never queried. It's sitting out there. And queries need to be fast. Unlike your analytical queries, like, hey, you can run a report and then wait for like an hour and then no big deal. But like when you're troubleshooting an incident at 2 a.m., it better be fast. And they do require like complex aggregations, yet speed is super important. So what are the requirements of an ideal solution? What do we want here? Observability is all about speed. Being able to resolve things quickly, getting answers fast for your questions. That's the purpose of observability, so that you can get in, get out as fast as possible. And it should be architected for cost efficiency from day one. It should not be kind of like something that's bolted on later. And no lock-ins. It should be simple. Migration should be simple. Customers should have like a lot of flexibility around what tools that they're using. And the lock-ins or like the selection of the tool should be based on the value that the tools offer, not based on the query language or the data locality, and being able to kind of like share the data with the customers or not. So here's a new opinionated approach. It's a new first principle approach, much like how Snowflake went after kind of like disrupting observability, disrupting data warehousing. Likewise, there is a unique opportunity with the new innovations in serverless and the separation of storage and compute in the observability land to deliver like much faster and much cheaper observability. It's an and, not an or. So we did some experiments, like we came up with like a new time series database exploiting these properties. So let's take a look at a brief look at this architecture, right? So the bold hypothesis here is that these new set of problems require a fundamentally new cloud-native architecture. If you look at this entire architecture, everything is stored in your object storage environment, and then you have like Lambda functions and no disks at all. And by having this unique architecture, you could pass on significant amount of cost savings back to the customers. The customers can store 10x more data and derive a lot more insights by slicing and dicing on high cardinality data with whatever granularity that you want. Being able to drill down by user ID, by customer ID, by device ID, by container ID, things like that are like not possible with the current systems. So what does this mean? What does this change from the previous typical observability stack that we have seen? There's a hot tier, there's a cold tier. There's nothing like that. Everything gets collapsed into the object storage. You can build a speed layer on top of like object storage that just answers your queries fast using serverless queries. And there are no disks at all. So what are some of the results looking like with this architecture, right? Any questions so far? Okay, let's keep going. It creates an opportunity to kind of like create like a dashboard-less debugging system with the AI native interface. You can just query whatever question that you have, and it results in kind of like much faster debugging. And you can say no to static dashboards. You can create dashboards on the fly, and you can slice and dice on any piece of data, on any cardinality. And it results in 10x lower compute costs. And how are you able to kind of like achieve this like 10x lower cost with this new architecture? because it's serverless. You only pay when you're using the dashboards, when you're running queries. It uses kind of like intelligent caching so that like the results are fast for like commonly accessed things like dashboards and alerts. And you can use like, you can avoid indexing completely, thus give the results like a lot faster. And the storage costs are also like a lot cheaper. It's like 24x like lower storage costs than storing them on cloud disks like EBS and things like that. If you were to use like a three-way replicated expensive SSDs. This is a cost per gigabyte. You're looking at around like 50 cents per gigabyte. S3 is like kind of like 24 times cheaper. And you can also leverage kind of like direct link technologies and availability zone affinity. Like you can leverage availability zone aware architectures to make sure that your networking costs are fixed and minimal. So there are no replication costs, and you can have like affinity towards kind of like your availability zones so that your egress costs are minimal. So let's pause here. So what do organizations need to do to stay ahead? Reevaluate your existing observability investments. Are you using current tools providing fast and actionable insights? Can they scale cost effectively as your systems become complex? Leverage AI for faster troubleshooting, especially for things like summarization of your incident resolution, summarized log insights, summarized anomaly insights, being able to kind of like use natural language to query and tune your alerts. Prioritize cost efficiency and scalability. Your observability systems should be able to give you sublinear pricing models so that like if your business were to grow by 2x, it should be, your cost should go in a sublinear fashion. Now the new architectures support that sort of like cost efficiency. Adopt modern cloud native architectures. And finally, demand simplicity from your observability systems or vendors. It should be an enabler, not an operational burden for you. It should support kind of like easy deployment and easy migration. I want to briefly summarize what I spoke about today. We spoke about like the key challenges with observability today: cost and speed of debugging. Getting both is hard, but the modern cloud native architectures that we have seen make it possible. We've also seen why the legacy architectures won't work for cloud native and AI workloads with the explosion of data and microservices. We talked about a new opinionated view of building a new time series database from ground up that can give like 5 times faster debugging experience when troubleshooting alerts, and it's also order of magnitude cost efficient. And we also talked briefly about like what organizations need to do to kind of like to stay ahead of the game in terms of like adopting modern cloud native architectures. A simple, it's a plug here. This is the only plug that I'll talk about. In case if you want to explore, all of this is kind of like live at play.oodle.ai. Thank you.
Questions? Okay, fine.
Okay, so how much of this are you actually saving and where for each piece? That is it seems like a bit of work for all of us to do in order to actually get observability that we get from new relevant.
Would you mind speaking with them?
Maybe I do. So that's a lot of work, it seems, for us. who are on either New Relic or Datadog or whatever we're at, in order to build out each of these lambdas, set up the, it looks like caching engine, a database, all these other pieces that are part of infrastructure. Because we still spend money on a database. Like I spend, $10,000 a month just on my own DBs. So, it all adds up. So storage might be a little bit of cost, but it seems like there's a lot more to it than that. Maybe you can explain where true cost savings is, and not just on S3, because there's a lot of more infrastructure that I see there.
Yeah. So you're right. So that's also reason why I think we build this system from ground up, so that we can offer that capability to our customers. But the core idea is that let's talk about what is it that gives us this unique capability, right? If you look at this entire architecture, there are no disks for the most part. It's mostly storage in the S3 buckets. And if you were to build this whole thing from ground up, I'm not sure if I would go recommend that. It's possible. What we're trying to allude to is actually, it's possible. You can get enterprise grade observability at open source cost, which is a current challenge today. And if you look at the cost savings are coming from querying layer in the Lambda functions here. All the querying happens on the Lambda functions on demand, and storage happens in the S3 buckets, which is 24x lower costs. And the data is we do not have any Kafka clusters. So that's also a big piece of costs in these legacy observability tools. And everything happens on demand. There's no indexing here, if you see this. So we built a custom storage format on top of S3, which gives you these queries a lot faster. But long story short, you should be building on your observability. You should not be investing in your own observability, building this whole system from ground up. Instead, use modern architectures or any vendors that support this modern architecture that can give you your Datadog, Splunk at a tenth of a cost. And so that way you can manage your data a lot more cost effectively. So does that answer your question?
Somewhat does, but there's no way I'm going to get a tenth of a cost. It's I spend what's the number now? Something about $10,000 a month on my Datadog bill.
Yeah.
No, on my New Relic bill a month. So you're saying I can go down to $1,000, maybe $2,000 bill by going to one of the vendors over there.
Yes, that's correct. I think we offer that. I think it's public pricing, and then you can actually see it live in the play.oodle.ai as well. So if you don't feel comfortable, I think we in that play.oodle.ai you see that where here is the workload that would cost this much dollars, and then you can actually play with it without creating an account.
Oh, great! And all these support OTel?
Yes.
Okay, I'll go check them out.
Yeah, that was a great talk. And I don't even have a question, but for the audience, I'm the founder of Icosic AI. We let you search through all of your server logs using natural language to get insights immediately in seconds rather than the hours you usually spend in your terminal. So if anyone's interested, catch me here. I'm here for about 10 minutes. Thank you.
Thank you. Any other questions? All right. Thank you very much.
Thank you very much. Yes.
Thank you.
We'll save somebody a lot of money.
first you can take my picture first, and then later on if you can take, sorry, I think that's, one second. Pull the other side. Oh, oh, I see. Oh, I see. You mean. Perfect. Thank you. Like if you can take the entire picture. Thank you so much. Yeah. If you can take something with the scale, this part. Yeah. So the closer ones, the bigger ones are fine. Yeah. Thank you. Cool. Thank you so much.
we do the same thing. Let's go. Where's Garrett?
You want to be as close to that side as you can. Yeah, that'd be perfect. Yeah, don't go this way. Okay. Yeah, cool. Because I can't get it all in the same shot. That's all. Cool. Yeah. Yeah. Just don't start wandering that way. That'd be good. Okay.
Hello. Hello. I'm the person that introduces you. Okay. Takes the microphone around if people have questions. Okay. So the question for you is, do you want to give your talk straight through with no questions, or do you want questions during your talk?
I think during the end would be...
At the end, okay.
Yeah, yeah, that's fine.
Okay, I'll tell everybody.
Actually, I think it depends on how many people show up, but I wouldn't mind it if it's... We have a lot of content, so...
Yeah. Yeah, from a timing perspective, we might not finish if people ask questions during.
Yeah, so let's do it at the end.
Fine. Okay. How do you say your name?
Jamie.
Jamie.
Yeah, it's just spelled with a Y, but it's like, you know,
Jamie.
Jamie with an I. Yeah.
Jamie with an I?
Yeah, same pronunciation.
I'm Manish.
Is there a clicker? Do you know if there's a clicker for changing slides?
Yeah, audio clicker. We both, because we're both presenting.
Let's see, let's see the audio. Okay, I don't see the clicker here, so maybe they just don't keep it here. Maybe this is it. Is there someone who will set up the audio?
Yes, I'll go tell them or say, do I have time?
Okay.
They're in the other building.
Yeah, that's okay.
Yeah, click that. Oh, I have time. Yeah, 15 minutes.
We'll start with 15
I'll
minutes.
go run over there and see.
Thank you. like, I was just here to make a call. I was looking for a quiet space to make a call. I think we'll have a.
Sorry? Do we have a room proctor in here for you?
There was a guy who was here, and he went. We asked him about the order, and he went.
Okay, good. Good. So who was that? Okay. Just making sure, because we had to swap volunteers around. I want to make sure you had somebody. Yeah. Okay.
Do you know where the clicker is?
Oh, the conference does not supply a clicker.
Okay.
Oh, okay. I can probably loan you one.
Otherwise, we'll be. Which is okay.
Because I was thinking
Yeah, you can try look it up.
Is this it? Should I just?
Yeah, you can try it. Probably a USB.
Oh, look at that.
Maybe pop it in quiet mode.
I can barely see it, and I don't see the cursor. Okay, I see it now. The problem is that now I cannot, like, if I'm narrating, I'm looking there, or I'm.
I think we can.
Yeah, mirror. We need to do like display settings.
You can do it here.
Yeah. Main display, use as mirror. Maybe check this. Yeah. Mirror. Oh, perfect.
Now we can put on the setting.
We can just go ahead and then, yeah, perfect. And now the slideshow. Yeah, that's perfect, right?
Do that.
Yeah.
See if we can get
Okay.
it picked up on. If we have to, we can do it here, I guess.
Yeah, that's okay.
Your laptop with you?
Uh,
Can I borrow your laptop?
I don't have. It's in the hotel.
Oh, who's this?
This is
Mine.
his.
Oh, can I see it for a second? Yeah.
People are coming. Josh, right? Josh. Josh Burgess. Josh Burgess. Yeah. Okay. Where do I find him? Maybe a booth or maybe a location.
Yeah, like.
Or maybe I find you somewhere and you can give it to him.
Yeah, find me, otherwise you will.
Where do I find you after the class?
Yeah, I'll hang around to find you.
Okay.
Okay. Sorry.
If I don't find you, we have a booth also.
Okay.
So tomorrow you can try to pick a booth or pick house.
Yeah, I'm doing tomorrow, but I'll.
Okay, yeah, just pick house. Whatever.
Manish came.
Okay. Yeah, maybe have the picker. We have the picker.
Test, test.
Okay. So where's convenient?
I guess here?
Yeah.
Yeah, the pocket.
This one is this one. There we go.
Okay. Jamie, you want to do this? Test, test, test. Okay, works. Test, test. This is it.
How do we connect it to the?
I have no idea. Maybe we
This
can.
right here is going to be your room proctor. And so
There should be a dongle you can connect it, and then you should.
Okay, we connect the dongle. USB-C?
USB-C? Yeah.
Like.
I see.
Oh, Jeremy, next door, we don't supply clickers.
Oh, we found one. Someone just nicely limited it here.
So you put it on the belt?
Yeah. Thank you. Now you probably have to.
Okay, there you go. I'm like, wait a minute. Yeah. It's running. Okay. Oh, this one's just one ear.
Okay. Okay.
Test. Can I sound test it? Okay, there.
Yeah, okay. Does it work? It's not working. Oh, it's working.
Which way is it?
So this is for their audio, but
yeah.
this is for the camera audio.
Yeah, okay. How do we do this? But it's two people talking.
I know, we only have one, so you'll just,
Yeah, okay. I'm just gonna.
so you can just clip it on. I think it travels pretty well.
Okay.
So just clip it to, just put it on this actually. Yeah.
It's gonna slide down.
Well, you don't go all the way.
crap.
Just pinch it like halfway, yeah.
Yeah.
There you go.
Okay.
Just try to keep it away from the, that's good. That's good enough. And it'll pick them up.
Interesting. Could you put that on for me?
Put what on?
This.
Oh,
It fell out.
Oh, yeah, that's weird. It's kind of hard to know. Let's see what we got here. Let's thread the needle. I got the trick to it. Okay, yeah, don't tug on it. There you go.
Thank you.
Cool, good. Make sure it's on? Yeah, it's on.
So we are starting in 5 minutes.
I just wanted to.
Yeah, check.
So it's down. Okay.
Yeah.
And then. Okay. This thing.
Okay. Yes. Manish. 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 Yes. The person who wrote this. It's his.
Okay. That's cool.
Demo? Oh.
No,
All slides.
You never do it like pulling up.
No.
Yeah, yeah, sure.
Off you go.
Yep.
I guess you have to coordinate with your camera.
Yeah, I think we're fine. They've already set up. Yeah, yeah. Hey. Good.
Have you got one? Might be handy. In case the throat breaks up. This one is really hard to stay on the air with.
Maybe you can just hold it.
Yeah, I'll just hold it if I need to.
Yeah. Okay, let me know when you're ready.
I'm ready. I think we could start.
2 minutes. I think we're good.
May as well get started. I mean,
yeah. Okay.
Hello, everybody. Welcome to the last talk of the day. Manish and Jamie will be presenting, and they would like you to hold your questions to the very end because they have heavy content, and save it for the end. Thank you.
All right. Can everyone hear me? Yes, I'm guessing. Yeah. Hi, everyone. My name is Manish. I work at a company called ClickHouse, and today we're going to be talking about Kubernetes, stateful sets, migrations, and so forth. So, quick introduction about me. I manage the auto-scaling team at ClickHouse. Jamie, you want to introduce yourself?
yes, I'm Jamie. I work in the auto-scaling team. I'm one of the software engineers in that team. Yeah.
Yeah. So we mostly do like vertical scaling, horizontal scaling, idling, scaling to zero of the database, and we're going to go into like the details of why that's relevant in the context of the migration that we're talking about. So this is the agenda. We're going to talk about auto-scaling in general and how it works inside ClickHouse. We're going to talk about a new approach to auto-scaling that we've been developing over the past couple of years, which what we like to call make before break. We're going to talk about what the migration is. So the make before break stuff is basically the context for the migration that we had to do, which contains of two parts, orchestration and execution. And then we're going to go into some of the challenges that we faced during the migration. So first of all, ClickHouse. I don't know, has anyone here heard of ClickHouse before? Oh, lots of hands. That's nice. Yeah, so for those who haven't, it's an open source, column-oriented distributed database. It's an OLAP database written in C++, known for its performance, analytical workloads. I guess most people know, but yeah, if you haven't tried it out yet, and if you're interested in like high-performance databases, so please check it out. So ClickHouse Cloud is our managed offering of ClickHouse. The company has been around for about 3+ years now. We provide like a serverless, fully managed experience. You can do like idling, scaling to zero. There's a separation of compute and storage, which is not available in the open source offering. And this is how it looks like, right? So the storage is disaggregated from the compute, and we basically use Kubernetes. So all the server replicas are deployed as Kubernetes pods that have PVCs attached to them. The PVCs contain metadata, so not any actual data. They're basically just a metadata pointing to the data that lives on S3 or any other object storage. And we're available on all three cloud providers. And for those of you who don't want to kind of run inside the fully managed offering, but just want to have the same experience inside your own virtual, virtual network, there's a BYOC offering that offers something very similar. And because like I mentioned, we run on Kubernetes, this is the very high-level architecture of what it looks like. So we have an operator, we wrote our own Kubernetes operator that manages those server pods. And of course, because it's a stateful service, like a database, not a web server, we use stateful sets to manage those pods. And we have like PVCs attached to that, which have the metadata. And the main resource here is the ClickHouse Cluster Custom resource. So why am I talking about auto-scaling? That's going to become relevant, but this whole problem started when we kind of started to do vertical scaling. And just to kind of set up the problem here, I'm going to give a high-level overview of what auto-scaling looks like inside ClickHouse Cloud and in Kubernetes autoscalers in general. So we have something called an autoscaler. you have a pod that you need to resize, right? Maybe it's like it's got 10 gigs of memory, you want to give it 20 gigs of memory, and that resize operation is only going to happen once the autoscaler does something which is called a pod eviction. It's going to kick a pod, which is going to get deleted, and then the controller, it could be any kind of a controller, in this case it's going to be the stateful set controller, is going to resubmit that pod, and that resubmission will resize the pod. Zooming in, how does that resizing actually happen? So when the pod eviction happens, here you can see and the controller resubmits the pod spec. That pod spec is getting intercepted by what we call a mutating webhook, which is like an admissions controller here. So this webhook is going to intercept the payload of that pod and then basically take the input from anything else. So in this case, you can see on the very left, we have like recommendations or the user's defined limits. So for example, I'm a user of the cluster, and I want to define the limit that, hey, instead of a 20 gig memory, I need 30 gigs or some other number. And that gets read into the mutating webhook, which will just mutate the spec and then resubmit it. And when the pod comes up, it's going to come up with a bigger size. So yeah, vertical scaling, this is what it's about, right? We want to go from some size could be CPU resources, could be memory resources, so some resource limit, which are starting, and then a target resource limit. And this is effectively what it looks like. This is what we want when we talk about vertically scaling a service. The problem with vertical scaling is in that by default, when you do vertical scaling inside Kubernetes, it's the model that we are calling the break first model. It's kind of implicit. That when you have like a disruption budget, in this case we have like a max unavailable equals 1, and you always want a disruption budget because otherwise you'll just have like complete unavailability for temporary duration, because remember, we are doing pod evictions, right? So every time you evict a pod, that pod becomes unavailable, it can't take any queries. While respecting the disruption budget, you want to do queries, and then effectively what this comes down to is a rolling restart of all the replicas that you have inside your cluster. And this is a very slow and painful process because, remember, there's queries running on these replicas. There could be backups, there could be long-running queries. You want to do like a graceful termination. You want to wait maybe, I don't know, 1 hour or some amount of time before you actually decide that the process is ready to safely terminate and then come up again. And the startup can also take some time, depending on how heavy a workload the cluster is running. So rolling restarts, they're slow. The other problem that happens with break first scaling is it causes a lot of pressure. So if you think about it, like, and you have like a workload running, and it suddenly requires more resources, which means more memory, more CPU. That's probably the worst time for you to actually take away a replica, right? So in this case, we can see the third replica is getting restarted. But the first two, of course, the workload probably hasn't changed. You should assume the worst, that the customer workload is probably just increasing. And that increased pressure, as well as the pressure from the third replica, is going to get redistributed to the other two. And when that happens, in the worst case, the remaining replicas can also just crumble under the pressure. So this is also a problem with this sort of a rolling restart model of scaling. So just to summarize, break first scaling is slow, it's disruptive, it puts pressure. And actually inside our cloud, what we've done is we've added like some sort of an extra overhead of memory and CPU resources just to combat that extra pressure that happens while the pod is undergoing the restart. And so to combat this, we started thinking about what we call the make before break scaling model. And here the idea is also pretty simple, right? So instead of doing a rolling restart and causing pod evictions, just add more replicas and then take away the old replicas, right? So in this case, we can see we added the 32 gig replicas and then immediately broke the 16 gig replicas. Why is this better? It's better because now you're not bounded by any sort of a termination. As soon as you add replicas, you immediately have that capacity available to actually contribute to the scaling. So when you need capacity, all you need to do is just add replicas and then take away the old ones. But you don't even need to take away the old ones for the customer's workload to start working. It's immediately available to you. So yeah, it's fast, it's not disruptive. You kind of also immediately got rid of the problem of the pressure during restarts. And if you do this mode of scaling, you immediately get rid of the extra overhead. So your allocation and your utilization can be very close to each other, which means your customers are not paying any extra for that overhead. This sounds like conceptually a very simple idea, but Kubernetes makes it surprisingly difficult to implement this idea, and I'm going to talk about that why. So a stateful set in Kubernetes, when it's actually undergoing scaling and adding and removing replicas, it's using an ordinal-based approach. So we have like a stateful set starting from ordinal 0, 1, 2. And if we think about this in a make-before-break approach, when we go to replicas, when we add replicas, which is the make part of our system, we can just do 3, 4, 5, and that's perfectly fine. But the minute we actually want to break replicas, we tell the stateful set, hey, please give me 3 replicas. It's going to go the other direction. So the arrow below, which is scaling in, it's going to remove replicas 3, 4, and 5, which is not what you want to do. You want to remove replicas 0, 1, and 2 in this diagram. And Kubernetes stateful sets don't allow you to do this. There is one hacky way of kind of bypassing this limitation, which is in this Kubernetes enhancement proposal, which is the start ordinal. So you can just always, for a stateful set, say, hey, instead of starting your replica ordinals at 0, start it at 1, and then start it at 2, and so on. But this kind of works, so it technically gives you the make-before-break mode of operating, but it has a problem. The problem is that maybe replica 0 is running a backup and you don't want to break it. Maybe replica 2 is running a query, you don't want to break it. You only want to break replica 1, which is currently kind of not doing too much, it's not that busy. It's something that's eligible to be broken. But you can't do that because the start ordinal, you can only break the replica 0. So it's only going to shift sequentially from left to right. So it's not flexible enough. So the problem is we want to break arbitrary pods, and that's something that's not available to you. We looked at some third-party controllers. So there's OpenCruise clone sets. There's advanced stateful sets. Those projects by themselves were not something we wanted to use, but we picked up a key idea from them, which was the idea of having delete slots. And this idea is pretty simple as well. You can just add a delete slot annotation, and then just your controller is going to read that delete slot and then just pick up and remove that replica arbitrarily. You're going to have to do some customization, but it's doable. So we wanted to use delete slots, but of course, delete slots are not an idea that is available inside the stateful sets in general. So we were kind of already approaching the point where we needed to make our own custom solution, which should look like a stateful set, right? Stable identity. We wanted to get rid of ordinals because of the problems I described before. And then have all the support of PVCs, respect the disruption budget. Topology spread constraints also became important, and we're going to talk about why. And so the approach to that was pretty simple. Instead of using a single stateful set, we wanted to use like what we have been calling multi-STS approach, which is we still want to have the stateful set. The vanilla stateful set from Kubernetes is very powerful. We want to leverage it. But instead of having one of those, we can just have many of those running at the same time. And there's actually a very good benefits to this, which is the stateful set controller is still going to be around. So the operator, the ClickHouse operator, is the code base that we change most often, and we did not want to introduce a lot of bugs while we don't want to kind of break the pods by accidentally introducing a bug. So the stateful set controller serves as kind of a layer between us. So even if the operator is doing something weird, the stateful set controller keeps reconciling the pods, and your server pods are still kind of stable. And in terms of code refactoring, it's also pretty nice that instead of using one, you can use many of the same thing instead of using a custom object. So it saved us up a lot of refactoring as well. And this is what it looks like. So this was the before thing. Before we were using a single stateful set, which was managing all 3 pods. And afterwards, we just added a bunch of stateful sets, right? So this allowed us to just immediately do the make before break or the MBB style of scaling, which is now you have these 3 stateful sets. You add a 4th one. This is the make step. And then you can just immediately break one. After there's going to be some synchronization, because remember, we're talking about a database here. We're talking about a multi-master asynchronous database that's taking inquiries. So there's going to be some catalog synchronization that's going to happen. And then we're going to just break this arbitrary replica. And that's it. And you do this 3 times, and or maybe you even do it in a single cycle. Instead of adding 1 replica, you just immediately add 3 replicas and then break the other 3. And then you're done. So why do we need migrations? Because we have a fleet of thousands of these single stateful set clusters. The customers are running their important workloads on them. We don't want to disrupt those workloads. But they still need to be migrated in order to leverage the faster, better way of scaling things. So hence this talk, which is about the migrations. And the first requirement of the migration was that we cannot have downtime. Why? Because we have other areas in which we needed to do other migrations, which are totally not relevant to this problem. But just as a product, we wanted to have like as minimum downtime as possible. No runtime would be perfect. There are going to be some sort of an orchestration requirements to this thing. It's not something you do in a single day. There's a lot of organizational overhead. You need to contact customers, all that stuff. You need visibility into this. Because this is the database operation, you're going to encounter strange issues while this is happening. Every time a customer, because customers are doing very strange things to the databases, so you're going to have like very unique issues. We're going to talk about those as well. And of course, because it's a migration, you should be able to roll it back. So no downtime via MBB. This is what it looks like, right? So a single stateful set managing 3 replicas. The funny thing here is even the migration itself is a make before break style of migration. So you make 3 extra stateful sets, and then you break, you do a sync, because now all these 6 replicas are kind of in synchronization. And then you break that first stateful set, which is managing the 3 pods. And at the end, you're just left with the 3 replicas. And this is kind of how you go from a single stateful set world to a multi-stateful set world without any downtime. So this was the approach which we wanted to orchestrate. The problem was, of course, that we did not want to kind of do this inside our own Kubernetes operator, because this is a one-time operation for a cluster. And after we are done with this, we need to kind of get rid of that code anyways. So we ended up writing our own custom migration controller. And we used a tool called Temporal. I don't know, how many of you have heard of Temporal? Yeah, some people. So Temporal is like an orchestration tool that we use to basically schedule these migrations. So let's talk about Temporal first. So the workflows in Temporal are kind of, I'm not sure of the slide, but yeah, this is kind of the better slide to introduce Temporal. So we have, it's something called a durable execution framework. So think of it like a job engine or a workflow engine, only the state is durable in the sense that you actually don't need to do any database operations. You don't need to say, okay, now please insert all my data into this database and then read from it. All of that is done for you. You just define your inputs, you define your outputs, and then things are persisted for you, which is very nice. It gives you a lot of other features out of the box, like failure detection, retries, timeouts. Gives you scheduling capabilities, so if you want to use it as a glorified cron job, you can. It's very composable, so you can compose different steps together inside the workflow, and it's very scalable. So workflow, what's a workflow inside? So these are just 2 terminologies I'm going to throw at you, a workflow and an activity. We're going to talk about workflows first. Workflow is basically like your job spec, right? It's a DAG or like a sequence of steps that you want to execute. Each individual step is called an activity, and what it does, it's basically a retriable thing. The very nice thing that it gave me, because remember, these migrations are something we wanted to almost babysit. We wanted to handhold these migrations, but at the same time have some sort of an automation. So it's interruptible, right? So you can always be in a place where you send something happens which you don't want to happen, but send a signal to an on-call engineer, and then pause the job right there. And then once you've kind of verified the situation, either abort or continue, which is a signal that the human can send back. So that's possible with this kind of a framework. And it can also have like child workflow. So you can have like one workflow running on every individual cluster, but then have like a parent which is managing all those workflows at the same time. And like I said, it can run on a schedule. So activities is the second kind of piece of jargon that I'm going to throw at you, which is the unit of work that is happening inside these workflows. So any kind of an external interaction, be it with an API, with a database, or a Kubernetes controller, all that work is actually happening inside these activities. And the durable part is actually defined right here. So when you define your inputs and outputs of an activity, those get persisted, and you can chain them together. So for example, the output of the first activity can become the input of the second activity, and that's how like kind of data moves through this workflow. So this is a very simple example of an activity, right? So here we're just getting an instance, and that's very simple. So we've defined our input, just a parameter of the Go function, and the output is the second, like the return value. And there's nothing else I'm doing here. There's nothing fancy, right? I don't know if I can use the clicker here. Yeah. So this part right here, which is where I'm executing the activity, that's it. It's just making an API call, and my inputs and outputs are persisted. And this is really important for one critical reason, which is after the migration was done, we wanted to kind of restore the cluster to the original state so that the customer has no idea of like, nothing has changed from their perspective. Their configurations, their settings are all kind of resetted back to the original state. And this is what it looks like. So when you execute like a workflow, if you read from the bottom to the top, this is like as the time goes on, more and more activities are added, and these results are basically the outputs in the JSON. We were using the cloud service, so this gives us a really nice view of what's happening, allows us to do like a lot of very useful debugging as well. And yeah, this is basically a whole like a DAG with the timeline view of how the workflow was executing as we were doing these migrations. Like I mentioned, signals are really important for human intervention. So here, for example, we detected a drift in our configurations during the migration. We send a message to Slack. Some engineer is going to take a look at this and then just going to send like a continue or an abort signal. And while that's happening, the workflow is basically just waiting for that approval or abort signal. I'm going to hand it over to Jamie to talk about the next part of the migration.
Cool. Thank you. So the first step of actually doing these migrations is organization and communication. Let me just attach this 1 second. So we need to make sure that communication to our customers about these migrations happens smoothly. If certain customers want to push back the migration, we need to track that. And our product team came up with a really nice tool to track this, a spreadsheet. So in general, in terms of organizing these migrations, one requirement that Manish mentioned earlier was we didn't want to have any downtime. We wanted inserts and queries from our customers to continue. But at the same time, we didn't want the customers to be able to do changes to their cluster that might affect our migration. So for example, we don't want them to change their auto-scaling settings in the middle of the migration, which could potentially cause issues. And it just simplified life for us if they didn't do this. So we built something called maintenance mode. I'll go a bit more into detail specifically into maintenance mode in a minute. But other things, we want to send them emails. We want them to see in the UI that 2 weeks before the migration happens, we let them know a migration will be coming so they're not surprised. When the migration's actually happening, we let them know. And then we had some questions for ourselves. How do we want to actually run these migrations? Should we do them all at once, spread them out? We could have concerns like cloud capacity and other issues. And so we decided to migrate them in batches. And we also encountered some issues, which we'll go into, which made us spread it out even further. So let's start with maintenance mode. So I mentioned we wanted something where we could prevent customers from changing the cluster. So auto-scaling settings, as I said, other API requests customers can make, maybe backups. And we didn't want to bill customers. We wanted to ensure that billing was disabled. So we decided to implement something generic that we could use on our cloud product, and we've used it for several other migrations and features. So we made this maintenance mode. In this particular migration that I'm talking about, we used partial maintenance. So that's showing there that we allow inserts and queries. So from a usability perspective of the cluster, they can still insert and query just as normal. This just shows an example. It's a bit of an old UI from ClickHouse because we started these migrations quite a while ago now. And just shows the banners and UI showing that maintenance mode is coming on the cluster, that there's a migration happening, and so on. So now let's get into the meat of how we actually did this migration from an implementation perspective. So Manish mentioned we had a migration controller. I'm going to go a bit in depth in exactly how that looked. So yeah, migration controller. So I just wanted to say this was a test in general for ClickHouse in terms of dynamically scaling, adding replicas, syncing the catalog, and by catalog I mean the databases and tables, and making sure that all works correctly. So that's one aspect. Second aspect for ClickHouse is while we have an S3 on our cloud service, S3 storage, the data is in S3, but the metadata at the time was on local EBS volumes. And if that data was lost, we don't know which of those blobs on S3 relate to which tables and databases. So if we lose that, it's data loss for the customer. So these are two things that we definitely don't want to go wrong during a migration. We don't want catalog inconsistencies on the tables and databases, and we don't want data loss. From our own code, in terms of the operator, we wanted to test, does multi-STS actually work? So this migration, as Manish described, is an MBB, make before break event. So we are actually going to add replicas and remove them and see if that all works. In terms of our migration controller, we wanted something where we could add a label, and this migration controller would take over, perform the migration. We wanted something that could be reversible if we needed to. If something went wrong with the migration, we could undo it and go back to this single stateful set mode. And we wanted something where we could handle this intermediary state where you have multi-stateful set pods, single stateful set pods, and we don't want to add this complexity to our main operator. We wanted something that could handle this intermediary state, know about both worlds, and perform this migration without additional complexity that we'd have to cover all cases in our operator where this backwards compatibility would need to be placed. So this is just an overview of the migration. Maybe I can show here. We have a ClickHouse CR, so this is the custom resource that these controllers would be reconciling. Our ClickHouse operator is normally reconciling a single stateful set. This migration controller will create these multi-stateful sets. We have a mutex so that we don't have both controllers trying to reconcile the CR at the same time. So that gives you like a high-level overview. But more specifically, how we actually implemented this is our migration controller is actually a wrapper controller around our normal operator reconciler. And the reason we did this is because when our operator does a bunch of things that we need to do for ClickHouse when we create these multi-stateful set pods. For example, we need to create users. We need to sync the catalog, databases, and tables. And we didn't want to re-implement all that. So the first thing that the migration controller does is just call the operator reconcile and create all these things. But then at the same time, all that complexity I mentioned in terms of the backwards compatibility, orchestrating this migration, deleting these single stateful set pods, being able to be reversible, that complexity could live in this migration controller, and it could coordinate this and call the functions from the main operator as needed. So that's why I call it a wrapper controller, if that makes sense. I'll also mention here, we didn't end up needing to use this, but we did have a PVC snapshot controller that snapshotted these PVCs. As I mentioned, the data is on S3, but the part metadata was on EBS volumes. And so just in case, before we drop these single stateful sets forever, we snapshotted in case we needed that for a recovery. But we didn't end up needing it. So yeah, to summarize on the migration controller, it's a wrapper controller around our main operator. It handled all of this very specific coordination we needed for the migration, and it's backwards compatible. Now, everything's great, right? We have our migration controller, we have temporal to coordinate this, and of course, we wrote a bunch of tests, and this is, I'll be the first to say our test pyramid is not perfect, but we did a bunch of tests, unit tests, end-to-end tests. We have something called Stress House internally at ClickHouse that does stress testing, and so there'll be no bugs, right? We won't have any issues. Well, unfortunately, when we went to production, we found a bunch of issues, and I'm going to tell you a few of those issues in detail. So the first one is this make before break. So over here on the left, we have the single stateful set pods, and over here on the right, we have the multi-stateful set pods. And just for some context, at ClickHouse, along with multiple other services in the world, we want to have some zone balance, and we want to make sure that we have a nice balance of availability zones from the cloud provider. So here we've got zones A and B, and here we've got 2 replicas with zone C. So this is a completely valid zone topology, and we want to maintain this max skew of 1. So we don't want to have a case where we have too many replicas in one particular zone. In case that zone goes down, then you have a problem, right? The problem with this is if you're using the Kubernetes pod topology spread, and then we, as you know, we remove the old replicas, these ones over here, at the end we end up with 2 replicas in zone C, which is now a problem, right? It's an invalid topology. If C goes down from the cloud provider, we have unavailability for our customer. So that's quite bad, right? Another example of this, also with regard to zones, we have a feature called idling. So clusters scale down if they're not used by a customer. And when we unidle those clusters, we might also do an MBB operation or a horizontal scale out. And before those PVCs are scheduled, the Kubernetes scheduler doesn't know what zone those PVCs could be in. So it could add a new replica. So over here we have a new replica in a zone that conflicts with an existing zone of a replica in the cluster and gives us an invalid topology. So we ended up deciding to implement something we call zone pinning in our operator. So we control the zones. We control it during horizontal scale, ins and outs. We control it through MBB operations. And There is a feature in Kubernetes now called match label sets where you could implement it that way, but at the time it wasn't available, so we decided just to move this logic into our operator. So this is now, we're moving into ClickHouse specific issues. So you're adding replicas, you're syncing the catalogs, databases, and tables, and you're removing replicas, and you can run into all kinds of issues doing that. And so the first issue was ClickHouse has something called an on-cluster DDL queue. So if someone, for example, creates a database or creates a table on cluster, it goes into this queue. And at the time of running that query, it records the host name of each replica that was active in the cluster at that specific time. Now, when we drop replicas from the cluster, they no longer exist. And ClickHouse was trying to resolve those DNS names and failing if there was any queries in the queue. So this was something where ClickHouse wasn't great at adaptively adding and removing replicas. We ended up fixing this in ClickHouse as part of this migration. Along similar lines, we had problems with external table engines. So specifically in ClickHouse, you can have an external data source, think something like Postgres or RabbitMQ, and you have a table in ClickHouse that refers to this external data source. Now, it makes a lot of sense that when you create this table, ClickHouse should check that this external data source is accessible and that it exists, and if it doesn't, it throws an error. The problem here is when you add, for example, a new replica during this make cycle, when you're adding 3 new replicas, it shouldn't actually check that because it's completely valid that you've turned off that external system temporarily. You're not actually creating the table, you're just adding a new replica. And when it tried to run those create table statements, it failed. So to fix this, ClickHouse now has a secondary attach where when a new replica is added, it's not treating it as the first time it's creating those tables, but rather attaching in tables that already exist and doesn't throw those errors. Again, along similar lines, ClickHouse has a feature that's very popular called materialized views, where you have a source table and a destination table, and you might have some trigger that causes a computation at insert time to do some aggregation on some data from that source table and inserts it into a destination table. And it's completely valid to delete that source table at some point, but still have the materialized view, the destination table. But when adding replicas, we were hitting a similar issue as the external table engines, where we get an error that that source table should exist. Again, this is just something that the maturity of ClickHouse in terms of adding and removing replicas improved through these migrations. Unbreakable replicas. Just one second. So Manish mentioned we have this sync stage where we want to sync all the part metadata. So we've added a replica, and before we remove the old replicas, we want to ensure everything's synced. So let's start with a situation where we have 6 replicas, we're receiving customer traffic, everything is great. And on the left side, we've got S1 to S3, which is the single stateful set clusters. Now, those clusters are being removed, but they're being dropped, and that process involves first removing them from the load balancer so they no longer receive any customer traffic. So that's the first step, and we do that so that when we sync the part metadata, there's no new inserts coming in from a customer, right? Now, we run a command called system sync replica lightweight. For example, here we're doing it on M2, one of the multi-stateful set pods. And what we want is to sync all the part metadata from all the other pods onto M2. So we want to make sure that everything's synced and we can safely drop S1 to S3. Now the issue is, in this example, both M1 and M3, the new pods, are receiving traffic. And ClickHouse is waiting for them to sync as well. Now if a customer's just consistently inserting into ClickHouse and there's always traffic, it'll never sync, or at least it will time out very frequently. So we solved this by adding a from modifier into ClickHouse for this query for system sync replica lightweight. So you can specify I want to sync from these specific replicas, in this case S1 to S3. So you can do system sync replica lightweight, S1, S2, S3. And then we're only waiting for these ones, which, as I said at the beginning, no longer receiving customer traffic, will be very quick to sync. So consistency of the DDL queue that I mentioned earlier, where the hostname issue popped up, we had a consistency issue where, because we're recording the host name of the replicas at the time the query is made, so you make a drop database query or a create database query, and we record the host names that exist at that moment, if this doesn't actually execute on one of the replicas that we're going to drop, then that query will just never execute anywhere, right? So we've got our new pods, the multi-stateful set pods. They don't have that host name in this list. It's never going to execute on them. And so how did we solve this? In our operator, we make sure that the queue is drained before we drop replicas. There is a better solution coming in our cloud product, which is an S3-based shared catalog, so that there isn't these replica local issues. So system tables is something common in many databases. ClickHouse has system tables. You can use them for introspection of ClickHouse. You can look at, for example, the query log or the metric log and see a lot of information about what's happening inside the database. Now, these are replica local. And as you can imagine, when you're doing this make before break operation, you're going to lose these system tables when clusters are dropped. And that's not great because it's useful to investigate these for data loss incidents. It's useful to look at it for historic metrics, for example, how queries performed in terms of memory and CPU and other dimensions. So for these migrations, we decided on a stopgap solution where we just copied this information during the sync phase. So in addition to system sync replica lightweight, to sync the part metadata, we also copied all of these system tables over. Now this wasn't great because if customers had huge system tables, many terabytes, we have to wait and copy all of that data. So this prompted the design of a new disk type in ClickHouse. There's a PR linked here, or an issue linked here. There's a PR now that's been merged. It's called S3 planar writable, and this is a disk that allows ClickHouse to attach those tables. So when we scale in replicas, for example, the single stateful set replicas and the examples we've shown, we would just attach those system tables without having to copy the data. So yeah, to close out this, I just wanted to mention that besides the technical challenges that we ran into that you see there, which caused some stop-starts, there's also the aspect that many customers don't want to do migrations for one reason or another. They're very scared of migrating their database if they have critical workloads. They might have some very important event that they rely on that database for. And so this causes issues where you have this huge long tail of customers who don't want to migrate. It gets pushed forward. And so this process took over 1 year to migrate a couple thousand clusters. And some migrations got stuck from those issues that I described for up to a week. So we had the situation where we had the single stateful set and multi-stateful set pods both existing for up to a week. And I think migrations in a database, for example, are super important because if you have data loss, it affects the product's reputation, right? So you need to take these seriously. Yeah. If anyone's got any questions, we can take those now. We're also at our booth tomorrow, so come and speak to us if you want to speak. We're hiring. We've got the Slack community if you want to join.
Hi, thanks for the talk. Tell me if I get this correctly from an architectural perspective or level. This is the migration here in order to be able to do vertical scaling. You are mutating your cluster. Have you considered instead creating a copy of the cluster? Assuming you're running in cloud, so you can have the shifting resources, creating another cluster, and then you can, for example, snapshot it. I understand that the data is in S3, so even snapshot from S3 instead of your EBSs, and then maybe do logical replication. And this also allows you, or the customer, if you expose it to the customer, to do like A/B testing to make sure that the new cluster is suited to the needs. So it allows you maybe less of technical issues with the mutation, but also some added benefits like A/B testing or horizontal scaling, having like more read throughput, etc.
Yeah, so I think firstly, we did consider this, and in fact, we had a migration from the table engine of replicated merge tree to shared merge tree that was very much in this manner with taking a backup, snapshot, and then restoring it into a new cluster. But a big motivation for the way we did the migrations is that this was a test of make before break, where we are adding replicas to ClickHouse and then removing replicas from ClickHouse, which is how our scaling will work going forward. And by testing this and finding those issues I described, it makes ClickHouse more elastic at scaling. So being able to add replicas and remove them quickly, finding those issues was really valuable to us, so that now we can, for example, do those scaling events and not hit this DNS issue or this external table engine issue, because we would have hit those when we actually enabled this form of scaling otherwise. So that was a reason that we did it the way we did.
Another issue would be that if we were to create a new cluster, we would need a way to kind of reroute the queries. Remember, this is a live migration, right? So when you're adding replicas to the same cluster, when the new TCP connections are made, we didn't mention it here, but we actually temporarily disabled the external connectivity from the old replicas that we are about to remove. So queries can still go to the new replicas. With a new cluster, instead of just adding replicas to the old one, we would need to find some way where all these two clusters can technically be part of the same ClickHouse cluster. And I don't think we do that because we have namespace-based isolation. So we would have to find a way around that as well. I don't know if you think about that.
Anyone else got anything?
All right. Cool. Thank you for attending the talk.
Thank you.
Thank you. Thank you very much.
Wait a second. You'll need this.